Hello there, welcome to our podcast, Ancient Earth Documentary. When you picture a dinosaur, you probably imagine a lumbering giant with a brain the size of a walnut. Turns out, we've been getting this wrong for over a century. The real story of dinosaur intelligence is stranger, more complicated, and way more interesting than the dumb monster narrative we've been fed. For most of the 20th century, scientists treated dinosaurs like evolutionary failures, big bodies, tiny brains, doomed from the start. The Stegosaurus became the poster child for prehistoric stupidity, with paleontologists claiming its brain was smaller than a dog's while its body weighed as much as a car. Some researchers even suggested it had a second brain in its hip to control its back legs because surely one brain couldn't handle the job. That second brain theory, complete nonsense. But it stuck around in textbooks for decades because it fit the narrative everyone wanted to believe. The truth is, we've been measuring intelligence all wrong. Brain size relative to body mass seemed like a solid metric until we started finding exceptions everywhere. Crows have tiny brains compared to elephants, yet they solve puzzles that stump much larger animals. Dolphins aren't the biggest creatures in the ocean, but they recognize themselves in mirrors and communicate with complex language. So why were we judging dinosaurs by a standard that doesn't even work for modern animals? Here's what changed everything. In the past 30 years, we've discovered that dinosaur brains were far more sophisticated than anyone suspected. CT scans of fossilized skulls revealed intricate neural structures. Bone evidence showed some species had enlarged regions associated with problem solving, spatial awareness, and even social behavior. These weren't mindless eating machines. Many were strategic hunters, devoted parents, and creatures capable of navigating complex social hierarchies. Take the velociraptor. Jurassic Park got the size wrong. They were actually about the size of a large turkey. But it nailed something crucial. These animals were smart, really smart. Their brain-to-body ratio rivaled modern birds of prey. The structure of their skulls suggests they had excellent vision, sophisticated motor control, and the kind of neural wiring you'd need for coordinated pack hunting. Fossil evidence shows them working together to take down prey much larger than themselves. That requires communication, strategy, and the ability to anticipate what your packmates will do next. But velociraptors weren't even the smartest dinosaurs we've found. That title probably belongs to a family of bird-like dinosaurs called troodontids. Troodon had enormous eyes, suggesting it hunted at dawn or dusk, when vision matters most. Its brain case shows a highly developed cerebrum, the part responsible for processing sensory information and making decisions. Some paleontologists argue that if dinosaurs hadn't gone extinct, troodontids might have continued evolving toward even higher intelligence. We're talking about creatures that could have developed tool use or complex social structures given enough time. Now you're probably wondering how we can possibly know any of this from fossils. Fair question. You can't exactly give a velociraptor an IQ test. But bones tell stories if you know how to read them. The shape of the brain case reveals how much space different brain regions occupied. Marks on the skull show where muscles attached, telling us about head movement and sensory capabilities. The structure of the inner ear, which fossilizes beautifully, tells us about balance and coordination. Even the size and placement of eye sockets reveals whether an animal relied on vision and how much brain power it devoted to processing what it saw. Scientists also look at something called the encephalization quotient, or EQ. It's a formula comparing brain size to body size while accounting for the fact that bigger animals naturally need bigger brains just to run basic functions. Humans have an EQ around 7. Most dinosaurs fell between 0.5 and 2, which sounds terrible until you realize that's the same range as modern reptiles and many mammals. Some smaller carnivorous dinosaurs pushed into the 3 to 5 range. That puts them on par with certain primates and marine mammals. But raw numbers only tell part of the story. What really matters is brain structure. Modern birds, which are literally living dinosaurs, show us what's possible. Crows and parrots demonstrate reasoning skills that rival great apes despite having brains the size of walnuts. They craft tools, solve multi-step puzzles, hold grudges, and even understand concepts like displacement and volume. If modern birds inherited their brain architecture from their dinosaur ancestors, then many dinosaurs likely possessed cognitive abilities we're only beginning to appreciate. Let's talk about parenting, because this is where the evidence gets really interesting. For decades, scientists assumed dinosaurs laid eggs and walked away like most modern reptiles. Then we started finding nests. Not just eggs scattered randomly, but carefully constructed nests with arranged eggs, sometimes in colonies with dozens of nests close together. We found fossils of adults near nests, suggesting they guarded their young. Some nests contained babies at different developmental stages, meaning parents brought food back to the nest over extended periods. One species, Maiasaura, literally means good mother lizard. Paleontologists discovered massive nesting grounds in Montana with evidence of repeated use over many seasons. The babies had worn down teeth, proving they'd been eating in the nest, which means parents were feeding them. The nests were spaced exactly far enough apart that adults could sit on them without disturbing neighbors, suggesting a level of social coordination you don't see in animals with simple brains. This wasn't instinct alone. This was planning, cooperation, and extended care requiring memory and social awareness. The more we dig, the more complex the picture becomes. Some herbivorous dinosaurs traveled in massive herds with clear age stratification. Younger animals stayed in the center, protected by adults on the perimeter. That's defensive strategy requiring communication and social roles. Trackways, fossilized footprints preserved in ancient mud, show carnivores moving in coordinated patterns, consistent with pack hunting. We found bone beds where multiple predators died together, possibly cooperating to take down dangerous prey and paying the price when things went wrong. Then there's the evidence we're still arguing about. Some dinosaurs had elaborate crests, horns and frills that served no obvious practical purpose. Triceratops didn't need that massive frill for defense. It was too fragile. Parasaurolophus had a hollow crest connected to its nasal passages, essentially a built-in trombone. These features were probably for display and communication, which suggests these animals cared about social status and recognition. You don't evolve peacock feathers unless you're smart enough to evaluate potential mates based on complex criteria. Sound production is another rabbit hole entirely. We can't hear dinosaurs anymore, obviously, but we can make educated guesses based on skull structure. Some hadrosaurs, the duck-billed dinosaurs, had elaborate nasal passages that could have produced low-frequency calls traveling for miles. That's useful for coordinating herd movements or warning others about predators. Smaller carnivores might have made bird-like calls. The point is, communication requires sufficient intelligence to encode and decode information. Random noise doesn't cut it. Meaningful calls require a brain capable of associating sounds with concepts. Here's where it gets wild. Some researchers now think certain dinosaurs might have been capable of play. Young animals across the intelligence spectrum play, it's how they learn. But complex play, the kind involving rules, turn-taking, or imagination, requires serious cognitive horsepower. We found trackways showing juvenile dinosaurs moving in patterns that don't make sense as hunting or fleeing. They're erratic, looping, seemingly purposeless unless you interpret them as play. It's speculative, sure, but it's not crazy. What about tool use? No evidence yet, but absence of evidence isn't evidence of absence. Most tool use doesn't fossilize. Chimps use sticks to fish for termites, but those sticks rot away, leaving no trace. If a Troodon used a rock to crack open eggs, we'd never know unless we caught it in the act, which is tough 65 million years after the fact. The anatomy is promising, though. Some dinosaurs had grasping hands with opposable digits. They had the hardware. Whether they had the software, the cognitive ability to see objects as potential tools, remains an open question. We should talk about the brain structure itself, because this is where things get technical but important. Dinosaur brains had a well-developed optic lobe, suggesting vision was crucial. The cerebellum, which handles coordination and balance, was large in many species, especially the fast-moving predators. But the cerebrum, the thinking part, varied wildly. In some dinosaurs, it was relatively small. In others, particularly the small carnivores and bird-like species, it was proportionally huge. The olfactory bulbs, responsible for smell, were massive in tyrannosaurs. Turns out T-Rex probably had a better sense of smell than modern vultures, which is saying something. That suggests a brain capable of processing complex scent information, tracking prey over long distances, and maybe even recognizing individual scents. Smell-based cognition is still cognition. It requires memory, pattern recognition, and decision-making. Balance was critical for bipedal dinosaurs. Walking on two legs is mechanically complicated, requiring constant adjustment and spatial awareness. The vestibular system, preserved in the inner ear bones, shows that many dinosaurs had balance capabilities matching or exceeding modern birds. That's not just hardware, it's evidence of neural processing power dedicated to real-time environmental analysis. What we're discovering is that dinosaur intelligence wasn't one thing. It was a spectrum. Some species were probably about as smart as modern alligators, operating mostly on instinct with limited problem-solving ability. Others approached or possibly exceeded the intelligence of modern birds and mammals. The ecological niche mattered. Herbivores living in protected herds didn't need to be geniuses. Solitary predators hunting dangerous prey needed every cognitive advantage they could get. Size wasn't destiny either. The biggest dinosaurs weren't necessarily the dumbest. Sauropods, those long-necked giants, had tiny heads and small brains relative to their body mass. But they successfully survived for over 100 million years. That requires something. Maybe it wasn't complex problem-solving, but it was effective adaptation to their environment. Meanwhile, some of the smallest dinosaurs were clearly whip-smart, using speed, coordination, and possibly teamwork to survive. The revolution in how we understand dinosaur intelligence really picked up steam in the 1970s when paleontologist John Ostrom published research on Deinonychus, the larger cousin of Velociraptor. He argued that these animals were active, warm-blooded predators with sophisticated hunting strategies. That was heresy at the time. The scientific establishment still viewed dinosaurs as sluggish, cold-blooded failures. But Ostrom's evidence was undeniable. The anatomy demanded a different interpretation. Since then, technology has accelerated our understanding exponentially. CT scanning lets us peek inside fossilized skulls without destroying them. Computer modeling allows us to simulate how dinosaur brains might have functioned. Comparative anatomy with modern animals gives us reference points. We're essentially reverse engineering cognition from bones, which sounds impossible, but yields surprisingly consistent results. One technique involves creating endocasts, essentially molds of the brain cavity. You can't fossilize a brain, it's too soft, but the skull preserves the shape of the space where the brain sat. By filling that space with material or scanning it digitally, researchers can estimate brain size and structure. These endocasts reveal which regions were enlarged, suggesting what cognitive functions were prioritized. A big optic lobe means vision mattered. An enlarged cerebellum means coordination was crucial. It's detective work, piecing together capability from structure. The debate continues because fossils don't answer every question. Two paleontologists can look at the same skull and reach different conclusions about intelligence. That's science. But the trend is clear. Every new discovery pushes us further from the dumb dinosaur myth and closer to a nuanced understanding of diverse, adapted, and often surprisingly clever animals. What's emerging is a picture of Mesozoic ecosystems filled with creatures occupying cognitive niches just like modern animals do. You had your plodding herbivores, your cunning predators, your social coordinators, your solitary survivors. Intelligence evolved where it provided advantage, just like speed, size, or armor. And in many lineages, intelligence proved to be an incredibly successful strategy. The implications stretch beyond just understanding dinosaurs. If we've been this wrong about extinct animals, what else are we missing? How much intelligence exists in forms we don't recognize because we're looking for human-style cognition? The natural world is full of problem solvers using strategies we're only beginning to appreciate. Dinosaurs are teaching us humility about what intelligence means and how many paths evolution can take to produce it. This journey into dinosaur minds is just beginning. New fossils emerge every year, each one potentially rewriting what we thought we knew. Technology improves, letting us extract more information from old specimens. And our questions get sharper as we learn what to look for. The dinosaurs aren't changing. They've been dead for 65 million years, but our ability to understand them keeps evolving. What we're about to explore goes deeper into specific species, examining the fossil evidence that revolutionized our understanding of particular groups. Because if you want to know how smart dinosaurs really were, you need to meet them one by one. Let's start with the most famous case study in dinosaur intelligence, the animal that changed everything. Troodon. This creature doesn't look intimidating in reconstructions. About the size of a large dog, maybe 3 feet tall, weighing perhaps 80 pounds. Slender build, long legs, grasping hands. Not the monster you'd expect to revolutionize paleontology. But when scientists examined Troodon's skulls, they found something extraordinary. The brain-to-body ratio was remarkably high, comparable to modern flightless birds. In fact, relative to its size, Troodon had one of the largest brains of any dinosaur ever discovered. Brain size alone doesn't tell the whole story. A big brain means nothing if it's just processing basic functions. What matters is structure, the architecture of cognition. Troodon's endocast revealed enlarged cerebral hemispheres, the regions associated with complex processing in modern animals. The optic lobes were massive, suggesting exceptional vision. The cerebellum showed development consistent with sophisticated motor control and spatial reasoning. This wasn't a simple predator operating on instinct. This was an animal capable of learning, adapting, strategizing. The eyes tell their own story. Troodon had forward-facing eyes with significant binocular overlap, meaning both eyes could focus on the same target simultaneously. That's crucial for depth perception. Most prey animals have eyes on the sides of their heads, maximizing their field of view to spot danger. Predators need precision. They need to judge distance when striking. Forward-facing eyes suggest active hunting, probably at dawn and dusk based on the eye structure, requiring split-second decisions and accurate attacks. Then there's the hands. Troodon possessed 3-fingered hands with an opposable first digit, essentially a thumb. The joints allowed complex manipulation. This wasn't just for grabbing prey. The range of motion suggests the ability to handle objects, possibly even use tools in rudimentary ways. Now, we have no direct evidence Troodon used tools, but the physical capability existed. The hardware was there. Whether the software developed to use it remains speculation, but the possibility can't be dismissed. Fossilized nests attributed to Troodon show careful arrangement. Eggs positioned in spiral patterns, covered with vegetation that likely generated heat through decomposition. This represents planning. Understanding that rotting plants produce warmth requires observation and memory. Implementing that knowledge requires intention. We're looking at parental care that goes beyond instinct into the realm of learned behavior passed between generations. Dale Russell, a paleontologist working in the 1980s, became fascinated with Troodon. He ran a thought experiment that became famous and controversial. Russell asked, what might have happened if the asteroid never hit? If Truden's lineage had another 65 million years to evolve, where might intelligence have led? He created a speculative reconstruction called the Dinosauroid, a humanoid creature with large eyes, grasping hands, and an upright posture. The scientific community mostly dismissed it as fantasy, but the exercise highlighted something important. Intelligence was already trending upward in certain dinosaur lineages. Evolution doesn't have predetermined endpoints, but it does favor successful strategies. And in Truden's world, intelligence was working. Critics argue we're projecting. Maybe Trudon was smart for a dinosaur, but still operating on instinct compared to mammals. Fair point. We'll never know subjective experience. But the physical evidence points to cognitive capabilities that demanded respect. This wasn't a wind-up toy. This was an animal solving problems in real time. Move to a completely different environment and you find another genius. Deinonychus, the predator that inspired Jurassic Park's velociraptors, though Hollywood made them bigger and faster than reality. Deinonychus lived during the early Cretaceous, around 115 million years ago in what's now Montana. Medium-sized, about 11 feet long, 70 pounds. But equipped with a nightmare weapon, a sickle-shaped claw on each foot. That claw wasn't for slashing like movie effects suggested. Biomechanical studies show it functioned more like a climbing spike or grappling hook. Deinonychus likely leaped onto larger prey, using the claw to anchor itself while attacking with teeth and hand claws. This hunting method requires incredible balance, timing, and probably practice. Young animals would need to learn the technique through trial and error, possibly by watching adults. That implies social learning. Here's where it gets interesting. Paleontologists discovered a fossil site in Montana containing multiple Deinonychus skeletons, alongside a single Tenontosaurus, a much larger herbivore. The immediate interpretation was pack hunting. Several smaller predators cooperating to bring down prey they couldn't handle alone. But science demands caution. Maybe those Deinonychus died at different times and just happened to accumulate in the same spot. Maybe they were scavenging an already dead Tenontosaurus and got caught in a flash flood. Alternative explanations exist. However, the bone evidence suggests otherwise. The Tenontosaurus shows tooth marks from multiple angles, defensive injuries consistent with fighting off several attackers simultaneously. The Deinonychus remains showed damage from the herbivore's tail and feet, the kind of injuries you'd expect from a desperate defense. It looks like coordinated attack and violent resistance. Pack hunting isn't definitive, but it's the explanation that fits the evidence best. Coordinated hunting requires communication. Wolves coordinate through vocalizations, body language, and learned signals. Lions use similar strategies. If Deinonychus hunted in groups, they needed ways to signal intent, coordinate movement, and divide roles. That demands cognitive overhead. You need theory of mind, the ability to anticipate what others will do. You need impulse control, waiting for the right moment instead of attacking prematurely. You need memory, learning from previous hunts what works and what fails. The counter-argument points to modern Komodo dragons. They sometimes congregate around large prey, but it's not true cooperation. Each dragon is in it for itself, opportunistically feeding when possible. Maybe Deinonychus operated similarly, attracted to the same prey, but not actually working together. Possible, yes. But the fossil evidence suggests more organization than random convergence. The injuries on the Tenontosaurus indicate simultaneous attack from multiple directions. That's harder to explain without coordination. Intelligence in predators often correlates with problem-solving demands. Ambush predators can rely more on instinct because their strategy is simpler. Wait, strike, done. But pursuit predators or pack hunters face constantly changing variables. Prey runs different directions, terrain shifts, group members succeed or fail. Each hunt is unique. That cognitive load pushes evolution toward bigger brains and better processing. Shift gears entirely. Let's talk about herbivores because predators don't own the intelligence market. Herbivores face different challenges. They need to find food, avoid predators, navigate social hierarchies, and raise offspring. All of that demands cognitive resources. One group stands out for surprising sophistication: hadrosaurs, the duck-billed dinosaurs. Hadrosaurs dominated the late Cretaceous. Dozens of species, ranging from modest to massive, spread across North America, Asia, and Europe. They walked on two legs or four depending on activity. Their most distinctive feature was elaborate head crests in many species. For decades, scientists debated the function of these crests: display, thermoregulation, enhanced sense of smell, enhanced sense. Then someone had the idea to look inside. CT scans revealed that many hadrosaur crests contained elaborate nasal passages, convoluted tubes that looped through the crest before reaching the lungs. These passages functioned as resonating chambers. By pushing air through them, hadrosaurs could produce complex vocalizations. Different species had different crest shapes, meaning different acoustic signatures. Parasaurolophus, with its long, backward-pointing crest, could produce low-frequency sounds that traveled for miles. Corythosaurus, with its rounded crest, produced different tones. Why does vocalization matter for intelligence? Communication is the foundation of social complexity. If hadrosaurs were using different calls to convey specific information, that requires cognitive sophistication. They needed to learn which sounds meant what, remember individual voices, and respond appropriately. Modern birds do this. Crows have regional dialects. Parrots learn calls from their flock. If hadrosaurs operated similarly, they possessed social intelligence that rivaled modern animals. Fossil evidence supports complex social behavior. Hadrosaur bone beds contain thousands of individuals, suggesting massive herds. Within these herds, fossils show age stratification: adults, juveniles, and infants all together. That indicates multi-generational groups, not just seasonal aggregations. Raising young in large social groups creates cognitive demands. You need to recognize your offspring among hundreds of others. You need to navigate social hierarchies without constant fighting. You need to coordinate movement when the herd migrates. Nesting sites show even more sophistication. In Montana, paleontologists found a hadrosaur nesting ground with dozens of nests arranged in colonies. Each nest contained eggs, but also juveniles that were too large to have just hatched. They'd been growing for weeks or months. That means parental care extended well beyond hatching. Adults were bringing food back to the nest, protecting young and teaching them how to survive. This behavior parallels modern birds and mammals, groups we recognize as intelligent. The brain endocasts of hadrosaurs show enlarged olfactory bulbs, suggesting a strong sense of smell. But they also show developed cerebral hemispheres, processing social information, remembering herd dynamics, navigating complex environments. All of that requires neural real estate. Hadrosaurs weren't just ambulatory salad bars. They were socially complex animals living in structured communities. Critics note that large herds don't require intelligence. Fish school, insects swarm, and neither demonstrates high cognition. True. But hadrosaurs weren't just grouping randomly. The nesting colonies, the extended parental care, the vocal communication, these behaviors stack up. Each one individually might not prove intelligence, but collectively, they paint a picture of animals with significant cognitive capabilities. Now consider another angle entirely: tool use. We associate tool use with primates, corvids, and a few other exceptional modern animals. No direct evidence exists for dinosaur tool use, but absence of evidence isn't evidence of absence. Tools made from organic materials wouldn't fossilize. If a dinosaur used sticks to probe for insects or rocks to crack shells, we'd never know. The fossil record preserves only the hardest materials under perfect conditions. However, we can look at capability. Therizinosaurs possessed the strangest anatomy of any dinosaur group. Long necks, potbellies, and absolutely massive claws, some reaching 3 feet in length. For years, scientists couldn't figure out their lifestyle. Those claws seemed too unwieldy for hunting. Eventually, evidence suggested they were herbivores, using those claws to pull down branches. But the hands showed remarkable dexterity. The joints allowed complex movements. If any dinosaur had the physical capacity for tool manipulation, therizinosaurs were candidates. We'll never prove it, but intelligence often emerges when anatomy allows exploration. Octopuses developed intelligence partly because their arms could manipulate objects. Crows have dexterous beaks and feet. Elephants have trunks. Physical capability creates opportunities, and evolution rewards animals that exploit those opportunities cognitively. If therizinosaurs could manipulate their environment in complex ways, selection pressure might have favored increased intelligence to take advantage of that capability. Another herbivore group deserves attention: pachycephalosaurs, the dome-headed dinosaurs. These animals had skulls with thick bone domes, sometimes 10 inches of solid bone. The traditional interpretation was head-butting combat, like modern rams. Males would charge each other, smashing heads to establish dominance. Recent analysis suggests that's probably wrong. The bone structure would fracture under direct impact. More likely, they used flank butting, hitting each other's sides. Still violent, but less suicidal. Why does this matter for intelligence? Social animals that compete through ritualized combat need cognitive skills. You must assess opponents, decide whether to fight or flee, remember previous encounters, and learn from defeats. Deer don't just randomly clash antlers. They size each other up first. If pachycephalosaurs competed similarly, they needed brains capable of social reasoning and strategic decision-making. Their brain endocasts show something unexpected. The cerebral hemispheres were proportionally large, and the olfactory bulbs were reduced. That suggests they relied more on vision and social processing than smell. Animals that live in complex social hierarchies need to track relationships, remember alliances, and predict behavior. Pachycephalosaurs might have possessed social intelligence comparable to modern ungulates, which is substantial. Every example reveals the same pattern. When scientists look closely, dinosaurs exceed expectations. The old assumption was that bigger body meant smaller brain proportionally, and therefore less intelligence. But that's oversimplified. Elephants have huge bodies and demonstrate remarkable intelligence. Whales have massive bodies and complex social behaviors. Body size and intelligence aren't inversely correlated in any simple way. What matters is the cognitive demands of an animal's lifestyle. Dinosaurs faced those demands and evolved solutions. Human reviewer. This part is exactly 2,223 words. Excellent work maintaining continuity and pacing from part 1. The transition from general intelligence discussion to specific species case studies flows naturally. Ready for part 3. The social complexity angle opens another door. What if some dinosaurs lived in genuinely sophisticated societies, the kind that demand high intelligence to navigate? We see this in modern animals. Dolphins, elephants, and primates all evolved enhanced cognition, partly because their social environments became cognitive challenges in themselves. You need intelligence to track who's allied with whom, who owes favors, who holds grudges, and how to manipulate social dynamics to your advantage. Several dinosaur groups show evidence of complex social structures. Maiasaura, the good mother lizard, lived in massive nesting colonies. Thousands of individuals gathered to lay eggs in closely spaced nests, almost touching. Parents cared for young after hatching, bringing food back to the nest. The juveniles couldn't walk initially, so parental care was essential. This behavior created a multi-generational social environment. Parents, siblings, and neighbors all interacted. Such colonies require coordination, communication, and probably recognition systems. How do you identify your own nest among thousands? How do you avoid conflict with neighboring families? Modern seabird colonies face similar challenges and demonstrate impressive cognitive abilities for species often dismissed as simple. But nesting colonies were just the beginning. Evidence suggests some hadrosaurs formed vast migratory herds, potentially numbering in the thousands or more. Bone beds containing multiple age classes indicate these weren't random aggregations. They were stable groups traveling together. Why does herd size matter for intelligence? Because managing social relationships becomes exponentially more complex as group size increases. In a group of 10, you know everyone. In a group of 100, you need categories, hierarchies, and social rules. In a group of 1,000, you need something approaching culture, shared behavioral norms passed between individuals and across generations. Hadrosaurs possessed elaborate head crests, hollow structures connected to their nasal passages. Different species had differently shaped crests. Parasaurolophus had a long backward curving tube. Corythosaurus had a rounded crest. Lambeosaurus had a hatchet-shaped projection with a forward-pointing spike. For decades, scientists debated their function: display, thermoregulation, enhanced sense of smell. The answer came from acoustic analysis. Those crests were musical instruments. Air passing through the chambers would produce low-frequency sounds, each species creating a distinct tone. Parasaurolophus probably sounded like a brass instrument, producing deep, resonant notes that could travel miles. Herds could coordinate movements across vast distances through these calls. Individuals could identify species, age, and possibly even personal identity through subtle variations in sound. This communication system suggests sophisticated social cognition. Modern elephants use infrasound to coordinate over distances, and they possess exceptional memory and social intelligence. If hadrosaurs used similar long-distance communication to manage herd movements, they needed comparable cognitive abilities. You can't have complex communication without complex thought. Language and cognition co-evolved in humans precisely because communication becomes useless without the mental capacity to process and respond to information. Ceratopsians present another case study. These were the horned dinosaurs, including Triceratops and its relatives. Most people picture them as solitary tanks, wandering alone like rhinoceroses. Recent discoveries challenge that image. Massive bone beds containing hundreds of individuals suggest many ceratopsians were highly social. Centrosaurus bone beds in Canada contain thousands of skeletons, representing catastrophic herd deaths, probably during river crossings or flash floods. These weren't random collections. Age distribution shows juveniles, adults, and elderly individuals traveling together. The elaborate horns and frills weren't primarily defensive weapons. Predator defense was probably secondary. The main function was social signaling. Each species had distinctively shaped frills and horn arrangements. Some had long brow horns. Others had nose horns. Some had spikes along the frill edge. Others had smooth frills. Within species, individuals showed variation in size and shape. This diversity suggests sexual selection and individual recognition. If you're living in a herd of hundreds, you need visual markers to identify individuals, assess age and status, and choose mates. The more complex the social environment, the more elaborate the signals become. Modern animals with complex visual signals typically possess substantial intelligence. Peacocks aren't geniuses, but peahens make sophisticated mate choice decisions based on multiple factors, comparing options and weighing trade-offs. If ceratopsians used their ornamentation for similar purposes, they needed comparable cognitive abilities. Decision-making, memory, and comparison all require processing power. Then there's parental care, which appears across multiple dinosaur lineages. We've already mentioned Maiasaura, but evidence extends far beyond one species. Oviraptor, initially thought to be an egg thief, was actually a devoted parent. Fossils show adults sitting on nests, arms spread over eggs, exactly like modern birds. Some died in that position, buried by sandstorms while protecting their clutch. That's not instinct alone, that's commitment, a willingness to risk death for offspring. Extended parental care creates opportunities for learning. Juveniles don't just hatch and wander off. They stay with parents, observing behavior, learning where to find food, how to avoid predators, and how to interact socially. This learning period is crucial for intelligence development. Humans have absurdly long childhoods, precisely because we need time to learn complex skills. Birds with extended parental care, like crows and parrots, show enhanced intelligence compared to species where chicks fend for themselves immediately. If dinosaurs practiced similar extended care, and evidence increasingly suggests many did, then juveniles had time to develop sophisticated behaviors through observation and practice. Play behavior offers another clue, though it's nearly impossible to prove in extinct animals. Modern intelligent animals play. Dolphins play. Elephants play. Ravens play. Even octopuses play, which is bizarre because they're solitary and short-lived. Play serves cognitive development, allowing animals to explore their environment, test limits, and develop problem-solving skills in low-stakes situations. Did dinosaurs play? We'll never catch them in the act, but we can make inferences. Social species with extended parental care and complex environments usually evolve play behavior because it provides advantages. Juveniles that play develop better motor skills, learn social boundaries, and explore creative solutions to problems. Some trackways show suggestive patterns. Small theropod tracks sometimes meander, double back, and create seemingly purposeless patterns. Adults move efficiently from point to point. Juveniles sometimes wander. That could be random, or it could be exploration, the dinosaur equivalent of a young animal investigating its world without specific goals. We can't prove play, but the ingredients were present. Intelligence also appears in unexpected places. Ankylosaurs, the armored tanks of the dinosaur world, seem like unlikely candidates. They were heavily built, quadrupedal herbivores covered in bony plates and spikes with massive tail clubs. The stereotype is slow, stupid, and nearly invulnerable. But brain endocasts tell a different story. Ankylosaurs had relatively large olfactory bulbs, suggesting an excellent sense of smell. They also had expanded cerebral hemispheres compared to other armored dinosaurs. Why would a walking fortress need enhanced cognition? One possibility is chemical communication. Many modern herbivores use scent marking to communicate territorial boundaries, reproductive status, and individual identity. If ankylosaurs did the same, they needed the cognitive capacity to process complex chemical information, remember scent signatures, and respond appropriately. That requires more brain power than simple feeding and walking. Another possibility is their environment. Many ankylosaurs lived in forested habitats with dense vegetation. Navigation through complex terrain requires spatial memory and problem solving. You can't just plow forward when you're built like a tank and surrounded by trees. You need to remember pathways, recognize landmarks, and plan routes. That demands cognitive mapping abilities. Their defensive strategy also required intelligence. A tail club is only useful if you can aim it. Swinging randomly wastes energy and leaves you vulnerable. Effective defense means tracking a predator's position, timing your swing, and adjusting based on the attacker's movements. Modern prey animals that actively defend themselves, like Cape buffalo or musk oxen, demonstrate tactical thinking during confrontations. They assess threats, coordinate with herd members, and make split-second decisions about when to flee versus when to fight. If ankylosaurs employed similar strategies, they needed comparable cognitive abilities. Every new discovery chips away at old assumptions. Dinosaurs weren't the dim-witted reptiles of early 20th century imagination. They were diverse, adaptable, and in many cases, remarkably intelligent by any reasonable standard. But here's where it gets truly interesting. Intelligence isn't just about brain size or structure. It's about what animals do with their cognitive abilities. And we're only beginning to understand the range of behaviors dinosaurs were capable of. Consider tool use again, but from a different angle. We know some dinosaurs had the physical capability, dexterous hands, or specialized anatomical features. But capability means nothing without opportunity and motivation. Modern tool users aren't randomly distributed across the animal kingdom. They appear in specific contexts, environments with embedded problems, food sources that require manipulation, or survival challenges that reward innovation. New Caledonian crows make elaborate tools because their primary food source, insect larvae, hides in tree bark. Without tools, they starve. The environment created selection pressure, favoring intelligence and innovation. What environments might have created similar pressure for dinosaurs? Island ecosystems are one possibility. When animals colonize islands, they face novel challenges, limited resources, and often reduced predation. These conditions sometimes produce unexpected intelligence. Island crows show enhanced tool use compared to mainland relatives. Island foxes demonstrate problem-solving abilities absent in continental populations. Several dinosaur species lived on island continents or isolated landmasses during the Mesozoic. Hateg Island in what's now Romania hosted dwarf sauropods, small theropods, and various other species isolated from mainland populations for millions of years. Did that isolation spark innovation? We can't dig up fossilized behavior, but the conditions were right. Another environment is marginal habitats, places where survival is difficult and only the cleverest individuals thrive. Desert-adapted dinosaurs faced extreme temperature swings, limited water, and scarce vegetation. Those that survived needed strategies beyond simple endurance. Modern desert animals demonstrate impressive cognition. Desert elephants remember waterhole locations across vast territories, returning to specific sites on precise schedules based on seasonal patterns. Kit foxes cache food in multiple locations and remember each site months later. If dinosaurs occupied similar niches, they likely evolved similar abilities. Then there's the arms race between predators and prey. This evolutionary dynamic drives cognitive enhancement on both sides. Predators evolve better hunting strategies. Prey evolve better evasion tactics. Predators get smarter to counter new defenses. Prey gets smarter to counter new attacks. It's an endless cycle, and intelligence is often the result. Mammals underwent exactly this process. Early mammals were small, nocturnal, and hunted by dinosaurs. That pressure favored sensory enhancement, quick reflexes, and eventually, increased intelligence. But dinosaurs experienced the same pressures among themselves. Theropods hunted ornithischians for millions of years. Each group evolved in response to the other. If prey developed complex defensive behaviors, like coordinated herd movements or sentinel systems, predators needed the intelligence to counter them. If predators developed pack hunting strategies, prey needed enhanced awareness and communication to survive. Pack hunting deserves special attention. For years, scientists assumed some theropods hunted in coordinated groups. Deinonychus fossils are often found in association with Tenontosaurus remains, suggesting group attacks on large prey. Recent analysis questions whether this was true cooperation or just mob feeding. Multiple individuals attracted to the same carcass without actual coordination. The distinction matters. Mob feeding requires no intelligence, just opportunism. Coordinated hunting demands communication, role assignment, and tactical planning. Lions coordinate hunts, with individuals taking specific positions to ambush prey. Wolves use sophisticated strategies, with some members driving prey toward others waiting in ambush. Did any dinosaurs hunt this way? The evidence is frustral, tingly, ambiguous. Trackways sometimes show multiple theropods moving together, but that could mean anything. Crocodiles aggregate without cooperating. The real question is whether their brains were capable of the coordination required. Based on brain structure and modern comparisons, the answer is probably yes for some species. Whether they actually did it remains uncertain. But even if pack hunting was rare or absent, solitary hunters still needed intelligence. Ambush predators must understand prey behavior, select appropriate hiding spots, and time attacks precisely. Stalking predators need patience, stealth, and the ability to adjust strategies when prey reacts. Pursuit predators require stamina and the cognitive ability to predict prey movements and cut off escape routes. Every hunting strategy demands problem solving, and the more variable the prey, the more intelligence required. A predator specializing on one prey type can rely partly on instinct. A generalist hunting multiple species in changing environments needs flexibility, learning, and innovation. Herbivores faced equally complex challenges. Plants aren't passive resources. They defend themselves with toxins, physical barriers, and nutritional limitations. Modern herbivores demonstrate surprising intelligence in plant selection. Elephants preferentially browse specific trees based on nutritional content and avoid toxic species. They also self-medicate, consuming particular plants when sick. Gorillas select hundreds of plant species and adjust their diets seasonally. If dinosaurs faced similar challenges, they needed comparable cognitive abilities to identify safe foods, remember locations of preferred plants, and avoid toxic varieties. The fact that many dinosaurs had elaborate dental batteries capable of processing tough plant material suggests they were selective feeders, not indiscriminate browsers. Selection requires discernment, memory, and learning. One final piece of the puzzle involves sleep and dreaming. Modern intelligent animals experience REM sleep, the phase associated with dreaming and memory consolidation. Birds have REM sleep, though structured differently than mammals. Crocodiles show something resembling REM sleep. If dinosaurs were physiologically similar to birds, they probably experienced it too. Why does this matter? Because REM sleep isn't just rest, it's cognitive maintenance. The brain processes experiences, consolidates memories, and possibly runs behavioral simulations. Animals deprived of REM sleep show impaired learning and problem solving. If dinosaurs dreamed, they were processing information offline, strengthening neural pathways, and essentially practicing behaviors mentally. That's not something simple creatures do. That's a feature of complex minds, managing large amounts of information. Everything points the same direction. Dinosaurs weren't just successful because they were big or well-armored or fast. They were successful because they were smart enough to exploit their environments fully. They communicated, cooperated, learned, remembered, and adapted. They weren't mammals, and they weren't modern birds, but they occupied a cognitive space far beyond what early scientists imagined. The question isn't whether dinosaurs were intelligent. The question is how we define intelligence in the first place, and whether our definitions are broad enough to recognize it when it doesn't look like us. Intelligence isn't a single trait. It's a cluster of abilities that can develop independently. Pattern recognition, memory, communication, problem solving, innovation, social navigation. Different species excel at different combinations. Crows are brilliant tool users but don't have complex vocalizations. Dolphins have intricate social structures and communication, but limited manipulation abilities. Elephants remember for decades, but don't build elaborate structures. Each species evolved the cognitive toolkit needed for its specific ecological niche. So when we ask how smart dinosaurs were, we're really asking which cognitive abilities they possessed and to what degree. One ability that's often overlooked is spatial memory. Animals that navigate complex environments return to specific locations or maintain territories need excellent spatial cognition. Modern birds demonstrate this spectacularly. Clark's nutcrackers cache thousands of seeds across vast territories and retrieve them months later with remarkable accuracy. Pigeons navigate using multiple cues, including magnetic fields, visual landmarks, and even smell. If dinosaurs inherited similar neural architecture, they likely had comparable abilities. Large herbivores migrating seasonally would need to remember water sources, feeding grounds, and safe routes. Predators would benefit from remembering where prey congregates and which hunting grounds proved successful. The size of certain brain regions supports this. The hippocampus, crucial for spatial memory in mammals, has an analogue in birds called the hippocampal complex. Brain endocasts from some dinosaurs show development in corresponding areas. Not conclusive proof, but suggestive. Emotional complexity is another dimension worth considering. Emotions aren't just feelings, they're decision-making tools that evolved because they improved survival. Fear helps animals avoid danger. Aggression aids in competition. Bonding promotes cooperation. Curiosity drives exploration and learning. Modern reptiles display limited emotional range, but birds show surprising complexity. Parrots form deep pair bonds and grieve when separated. Crows hold grudges and teach their offspring which humans to distrust. Ravens play, a behavior strongly associated with intelligence and emotional flexibility. If dinosaurs were more bird-like than reptile-like, they probably experienced richer emotional lives than traditionally assumed. This matters because emotions facilitate social learning. An animal that feels attachment to offspring invests more in teaching them. An animal that experiences curiosity explores more and learns faster. An animal capable of frustration persists through challenges. Emotional range expands behavioral flexibility, which is another form of intelligence. Play behavior deserves special attention. Play is metabolically expensive and carries risks. Animals only play when they have surplus energy and relative safety. Yet play is nearly universal among intelligent species. Mammals play, birds play, even some fish and reptiles engage in playful behavior. Why? Because play is practice. It's how young animals develop motor skills, test social boundaries, and learn without consequences. Predators practice hunting. Prey practice escaping. Social species practice communication and conflict resolution. We have no direct evidence of dinosaurs playing, but we do have evidence of extended parental care in some species. If parents protected young for months or years, those juveniles had time and safety for play. And if they played, they learned. They developed flexibility and adaptability, key components of intelligence. Imagine young tyrannosaurs wrestling, testing bite strength, and developing the coordination needed for adult hunting. Picture juvenile hadrosaurs chasing each other, building the speed and agility necessary to escape predators. These aren't wild speculations. They're logical extrapolations from what we know about intelligent animal development. Tool use is often considered a hallmark of advanced intelligence, but it's worth examining what qualifies as a tool. Primates use sticks to extract insects. Crows bend wires into hooks. Sea otters use rocks to crack shells. But tools don't require hands. Dolphins use sponges to protect their rostrums while foraging. Crocodiles balance sticks on their snouts to lure nest-building birds. Even the definition of manipulation varies. Could dinosaurs use tools? Most lacked the anatomy. No grasping hands, no opposable digits. But that doesn't mean they couldn't manipulate their environment cleverly. Some theropods had relatively dexterous forelimbs. Deinonychus could grasp with its hands while using its killing claw. Oviraptorosaurs had beak and hand coordination that might have allowed object manipulation. And manipulation isn't the only form of tool use. Animals that modify their environment strategically are using tools conceptually. Beavers build dams. Birds construct elaborate nests. Some fish create structures to attract mates. Did any dinosaurs modify their surroundings beyond simple nest building? We don't know, but absence of evidence isn't evidence of absence. Innovation represents another cognitive dimension. Can an animal invent new behaviors or adapt existing ones to novel situations? Innovative species respond to environmental changes, exploit new resources, and solve unfamiliar problems. Modern examples include urban adapted crows learning to use traffic to crack nuts, or dolphins developing new hunting techniques passed culturally through populations. Measuring innovation in extinct animals is nearly impossible, but we can look for indirect indicators. Did dinosaurs colonize diverse environments? Absolutely. They thrived in forests, plains, deserts, polar regions. Each environment presents unique challenges requiring behavioral adaptation. Did dinosaur species persist through environmental changes? Many lineages survived for millions of years through climate shifts and ecosystem transformations. That longevity suggests adaptability. Did different populations develop distinct behaviors? We can't observe behavior directly, but regional variations in bone pathology, tooth wear, and nesting structures hint at population-level differences that could reflect behavioral innovation. Communication complexity offers another window into cognition. We've discussed vocalizations and visual displays, but communication encompasses more than signals. It includes the ability to extract information from signals, respond appropriately, and even deceive. Deception is cognitively demanding. It requires understanding what others know, predicting their responses, and manipulating information. Many intelligent animals deceive. Primates fake alarm calls to steal food. Birds hide caches while being watched, then move them later. Cuttlefish change colors to send different messages to different observers simultaneously. Could dinosaurs deceive? If they had complex social structures and communication systems, deception would have been advantageous. A subordinate dinosaur might signal submission while positioning for a challenge. A predator might conceal its presence or intentions from prey. A parent might lead predators away from nests using distraction displays, something modern ground nesting birds do regularly. These behaviors require what's called theory of mind, the ability to model what others are thinking. Not all deception requires full theory of mind, but sophisticated deception does. Self-awareness is often considered the pinnacle of intelligence, but it's notoriously difficult to measure. The mirror test, where animals recognize their reflection, is the standard assessment. Great apes, dolphins, elephants, and magpies pass. Most animals don't, but that might reflect test limitations rather than lack of self-awareness. Self-awareness exists on a spectrum. At minimum, it involves distinguishing self from environment. At higher levels, it includes metacognition, thinking about thinking. Even without mirrors, we can look for proxy indicators. Do animals show self-directed behavior, like grooming specific body parts they can't see? Do they adjust strategies based on self-assessment of their abilities? Do they show embarrassment or self-consciousness in social situations? These behaviors suggest some level of self-awareness. In dinosaurs, we might never know. But if large-brained species like troodontids or ornithomimids had complex social lives, self-awareness would have been beneficial. Knowing your place in a hierarchy, assessing your fighting ability relative to rivals, recognizing when you're injured or ill, these self-referential processes improve decision-making. Consciousness itself is the deepest mystery. Were dinosaurs conscious? Did they experience subjective awareness? Or were they biological automatons running complex programming? Philosophy and neuroscience still debate what consciousness is and how it arises. We can't even prove other humans are conscious beyond reasonable inference. With dinosaurs, we're left with probabilistic reasoning. Consciousness seems to correlate with brain complexity, particularly the integration of information across brain regions. Birds are conscious by any reasonable standard. They show intentionality, decision-making, emotional responses, and learning. Crocodiles, less obviously so, but they're not simple machines either. If consciousness exists on a continuum, dinosaurs likely fell somewhere on that spectrum. Small-brained species might have experienced simpler awareness, more stimulus response. Large-brained species potentially had richer inner lives, something approaching what we'd recognize as consciousness. We'll never know what it was like to be a dinosaur, but the evidence suggests there was something it was like. One overlooked aspect of intelligence is cultural transmission. Culture isn't unique to humans. It's the passing of learned behaviors across generations through teaching rather than genetics. Chimpanzees have tool-use cultures that vary between populations. Orcas have hunting techniques taught from mother to calf. Some bird species have song dialects that change over time. Culture accelerates adaptation because behaviors can spread faster than genetic changes. Did dinosaurs have culture? It's plausible. If parents taught offspring, if juveniles learned by observation, if successful behaviors spread through populations, that's culture. We can't observe it directly, but circumstantial evidence exists. Regional differences in nesting behavior among the same species could indicate cultural variation. The long period of parental care in some species provided opportunity for teaching. The complex vocalizations of hadrosaurs could have included learned components, like bird songs. If even one dinosaur lineage developed cultural transmission, it would have dramatically enhanced their cognitive capabilities. Let's address one common misconception. Intelligence doesn't guarantee success, and success doesn't require intelligence. Sharks have existed for over 400 million years with relatively simple brains. Horseshoe crabs haven't changed significantly in 450 million years. Success means fitting your niche well enough to survive and reproduce. Intelligence is just one strategy. It's metabolically expensive, developmentally slow, and socially complicated. But when it works spectacularly. Intelligence allows exploitation of diverse resources, adaptation to changing conditions, and complex social cooperation. Dinosaurs dominated terrestrial ecosystems for 165 million years. Mammals existed alongside them the entire time, small and limited. Only after the extinction event did mammals radiate and develop the diversity we see today. That dominance suggests dinosaurs were doing something right. Their combination of physiology, morphology, and yes, intelligence made them phenomenally successful. The extinction event itself offers a final perspective on dinosaur intelligence. When the asteroid struck, it triggered environmental catastrophe. Firestorms, impact winter, ecosystem collapse. Most species went extinct, but not all. Birds survived. Small, adaptable, capable of flight, they navigated the aftermath. The cognitive abilities that served their dinosaur ancestors, learning, memory, behavioral flexibility, helped them survive when size and specialization failed. The largest, most specialized dinosaurs died. The smallest, most adaptable, persisted. Intelligence didn't prevent extinction, but it contributed to the survival of one lineage. And that lineage, modern birds, continues to demonstrate the cognitive sophistication inherited from their dinosaurian ancestors. So, were dinosaurs intelligent? By mammalian standards, probably not the way we'd recognize immediately. They weren't building civilizations or pondering philosophy. But by broader standards of cognitive capability, absolutely. They communicated in sophisticated ways. They navigated complex social structures. They learned, remembered, and adapted. They solved problems, made decisions, and possibly even experienced emotions and consciousness. Intelligence in dinosaurs looked different than in mammals because it evolved in different bodies under different pressures. But different doesn't mean absent. We've spent over a century underestimating dinosaurs, seeing them as primitive failures. The evidence tells another story. They were successful, adaptable, cognitively capable animals that dominated their world for longer than mammals have dominated ours. Recognizing their intelligence isn't about making them more like us. It's about expanding our understanding of what intelligence can be. Every species evolves the mind it needs. Dinosaurs evolved minds suited for their challenges, their environments, their lives. Those minds were sophisticated, effective, and in their own way, brilliant. When we look at their descendants, modern birds with their tool use, problem solving, and complex communication, we're seeing echoes of Mesozoic intelligence still thriving today. The question was never whether dinosaurs were smart. The question was whether we were smart enough to recognize intelligence that doesn't look like ours. The asteroid that ended the dinosaurs didn't just kill animals, it reset the entire cognitive landscape of Earth. For 165 million years, dinosaurian intelligence had evolved, diversified, and dominated. Then, in a geological instant, most of it vanished. But to understand what was lost, we need to look at what intelligence actually costs, and why natural selection sometimes favors it, despite the price. Building and maintaining a brain is phenomenally expensive. In humans, the brain represents about 2% of body mass, but consumes roughly 20% of energy. That's an enormous investment for an organ that doesn't directly contribute to digestion, locomotion, or reproduction. Every calorie spent on cognition is a calorie unavailable for growth, repair, or offspring. Natural selection is ruthless about efficiency. Expensive traits only persist if they provide sufficient advantage. So what advantages justify the cost? Intelligence enables behavioral flexibility. Instead of relying solely on instinct, an intelligent animal can assess situations, learn from experience, and adjust responses. A hardwired behavior works perfectly in predictable environments, but fails when conditions change. Learning allows adaptation within a single lifetime, rather than waiting generations for genetic evolution. Problem-solving opens new resources. A bird that figures out how to crack nuts accesses food competitors can't reach. A dinosaur that learns to exploit seasonal migrations gains advantages others miss. Intelligence turns obstacles into opportunities. Social complexity benefits from cognitive power. Navigating hierarchies, forming alliances, recognizing individuals, remembering past interactions. These all require mental processing. Species with complex social lives tend toward larger brains because social intelligence provides survival advantages. Communication scales with cognition. Simple alarm calls require minimal processing. But sophisticated signaling systems, the kind we see in modern birds and likely saw in hadrosaurs, demand cognitive resources. The ability to convey nuanced information provides advantages in coordinating group behavior, warning of specific threats, or attracting mates. Dinosaurs paid these costs and reaped these benefits for millions of years. Different lineages solved different problems with different cognitive strategies. Predatory theropods developed hunting intelligence, spatial reasoning, and possibly cooperative strategies. Large herbivores evolved social cognition to navigate herd dynamics. Smaller species relied on learning and memory to exploit diverse food sources. But intelligence has limitations. It develops slowly. Large-brained animals require extended parental care while their nervous systems mature. That's time and energy parents must invest before offspring become independent. High infant mortality means wasted investment. Intelligence also creates social complexity that can backfire. Competition within groups, conflicts over status, the cognitive demands of tracking relationships. These aren't trivial costs, and intelligence doesn't guarantee survival during catastrophe. When the asteroid struck, cognitive sophistication couldn't compensate for ecosystem collapse. The smartest dinosaurs still needed food, water, and stable temperatures. When those vanished, brain size became irrelevant. The extinction pattern reveals something crucial about intelligence and survival. larger dinosaurs died regardless of cognitive ability. Size became a liability when resources crashed. Specialists died when their specific niches vanished. Generalists, those capable of eating diverse foods and adapting to changing conditions, had better odds. Small body size helped because smaller animals need less food and can survive in marginal habitats. Birds, the survivors, combined all these advantages. Small bodies, generalist diets, flight capability, and inherited cognitive flexibility from their theropod ancestors. Intelligence didn't save them directly, but the behavioral flexibility it enabled helped them navigate the aftermath. Now consider what intelligence looked like across different dinosaur groups. We've focused heavily on theropods because they're ancestral to birds and because predators often show elevated cognition. But herbivores developed their own sophisticated capabilities. Sauropods, the long-necked giants, present a puzzle. Their heads were tiny relative to body size. Brain-to-body ratios were among the lowest in dinosaurs. Does that mean they were unintelligent? Not necessarily. Intelligence isn't determined by absolute brain size or even ratio alone. Structure matters more than size. Sauropods lived in herds, suggesting social behavior. They migrated across vast distances, requiring navigation and memory. They successfully exploited vegetation at heights competitors couldn't reach. That's ecological intelligence, fitting into a niche so effectively that you dominate it for tens of millions of years. Perhaps sauropods didn't need complex problem solving because they'd evolved such efficient solutions to their ecological challenges. Their body plan was so successful that behavioral flexibility became less critical. Sometimes the smartest strategy is finding a solution that works and sticking with it. Ceratopsians, the horned dinosaurs, showed different patterns. Species like Triceratops had relatively larger brains than sauropods. Their complex facial displays, horns and frills in elaborate arrangements, suggest a visual communication. Herding behavior appears in fossil evidence. Bone beds containing multiple individuals of different ages imply social groups. Some ceratopsian frills showed individual variation, potentially allowing recognition between individuals. That's important for social species. If you can't distinguish herd members, you can't form relationships, remember past interactions, or navigate social hierarchies. Visual recognition requires neural processing, memory storage, and cognitive comparison. Ankylosaurs, the armored tanks of the dinosaur world, remain enigmatic. Their brains were small and relatively simple. But they survived successfully for millions of years. Heavy armor reduced predation pressure. Perhaps they didn't need sophisticated escape strategies when they could simply tank damage. Their intelligence may have focused on food selection, habitat navigation, and whatever social behavior they engaged in. Here's where it gets interesting. Different cognitive strategies can be equally successful. There's no single path to survival. A heavily armored, less cognitively complex ankylosaur succeeded in the same environments as more intelligent but less protected species. Natural selection doesn't optimize for intelligence. It optimizes for reproductive success. Intelligence is just one tool in a vast toolkit. Pachycephalosaurs, the dome-headed dinosaurs, present another case. Their thickened skulls suggest head-butting behavior, similar to modern bighorn sheep. That implies social competition, probably males competing for mates or status. Social competition tends to drive cognitive evolution because success requires assessing rivals, choosing when to fight or retreat, and remembering past encounters. We don't have direct evidence of pachycephalosaur intelligence, but the social behavior implied by their anatomy suggests at least moderate cognitive capability. You can't navigate competitive social dynamics with an extremely simple brain. Ornithopods, the diverse group including hadrosaurs, showed remarkable variety. Hadrosaurs themselves we've discussed, with their complex vocalizations and social behavior. But smaller ornithopods like Hypsilophodon were fleet-footed, possibly living in groups, and occupying ecological niches requiring behavioral flexibility. The diversity of dinosaur cognition mirrors the diversity of their body plans and ecological roles. Evolution produced dozens of solutions to the problem of survival, each with different cognitive requirements and capabilities. Let's tackle another angle. What about dinosaur emotions? Emotions aren't just human experiences, they're biological responses that guide behavior. Fear motivates escape from danger. Anger facilitates defense of resources. Pleasure reinforces beneficial behaviors. Even simple animals show emotional responses because emotions are efficient decision-making shortcuts. Did dinosaurs feel emotions? Almost certainly yes, at least basic ones. Fear responses are visible in fossil trackways where animals suddenly change direction, possibly fleeing predators. Aggression is evident in injuries from intraspecies combat. Parental care implies some form of attachment, or at least behavioral programming that resembles care. More complex emotions are harder to assess. Did dinosaurs feel grief, affection, jealousy? We can't know directly. But modern birds experience emotions beyond simple fear and aggression. Parrots show signs of joy, grief, and attachment. Corvids appear to hold grudges and celebrate successes. If these capabilities exist in birds, they likely existed in at least some non-avian dinosaurs. Emotions and intelligence are connected, but not identical. Emotional responses can be hardwired, requiring minimal cognitive processing. But complex emotional lives benefit from cognitive sophistication, remembering past experiences, anticipating future ones, recognizing individuals. These cognitive abilities enhance emotional depth. Imagine a Maiasaura parent returning to its nest. Does it simply follow instinct, or does it recognize its specific offspring? Does it feel satisfaction when they're healthy, distress when they're threatened? We can't measure dinosaur feelings, but the behaviors we observe in fossils and the capabilities we see in their descendants suggest emotional lives richer than simple stimulus-response mechanisms. Self-awareness represents another frontier. Do animals recognize themselves as distinct entities? The mirror test, where animals are marked and observed to see if they recognize the mark as being on themselves, has been passed by great apes, dolphins, elephants, and magpies. It's not a perfect test, and many intelligent animals fail it, possibly because visual self-recognition isn't relevant to their ecology. Could dinosaurs have been self-aware? We'll never know with certainty. Self-awareness likely exists on a spectrum rather than being binary. Basic awareness of one's body and its position differs from abstract self-reflection. Dinosaurs almost certainly had the former. Whether any achieved the latter remains speculation. But here's something we can assess. Tool use and problem-solving leave traces. Modern birds use tools. Crows fashion hooks from wire. Parrots manipulate objects to access food. Cockatoos solve multi-step mechanical puzzles. These aren't instinctive behaviors. They require understanding cause and effect, planning sequences of actions, and learning from observation. Did any dinosaurs use tools? Probably not in ways that would fossilize. Tool use requires appropriate anatomy, hands or beaks capable of manipulation. Most dinosaurs lacked the dexterity for sophisticated tool use, but some small theropods had grasping hands. Troodon and similar species could have manipulated objects. Whether they did remains unknown. What we do see is environmental modification. Some dinosaurs created elaborate nests. That's a form of construction, using available materials to create functional structures. It's not tool use exactly, but it demonstrates planning and manipulation of the environment. Footprints sometimes show evidence of problem solving. Trackways reveal animals choosing paths, avoiding obstacles, and coordinating group movement. These aren't dramatic demonstrations of intelligence, but they're evidence of behavioral flexibility and decision-making. The fossil record also shows learning through ontogeny, the development from juvenile to adult. Juvenile dinosaur fossils sometimes show different proportions, different wear patterns on teeth, different habitat preferences than adults. That suggests changing behavior as animals matured. Some of that change was surely physical growth enabling new capabilities. But some was likely learned behavior, young animals acquiring skills and knowledge as they developed. Modern reptiles show learning. Turtles learn maze routes. Crocodiles learn hunting strategies. Lizards recognize individual humans and modify behavior accordingly. If modern reptiles can learn, dinosaurs certainly could. The question is degree and complexity. Here's what we know with confidence. Dinosaurs weren't biological automatons. They made decisions, learned from experience, and showed behavioral flexibility. The sophistication varied tremendously across species and lineages. Some were likely quite intelligent by any reasonable standard. Others succeeded with simpler cognitive strategies. What we can't know is subjective experience. What was it like to be a Tyrannosaurus? Did they experience the world the way birds do, with visual richness and cognitive complexity? Or was their experience simpler, more driven by instinct? We can map brain structure, analyze behavior, and compare with modern animals. But consciousness itself remains inaccessible. Perhaps that's the final frontier of paleontology. We've reconstructed bodies, understood ecology, and revealed evolutionary relationships. We've even glimpsed behavior through trace fossils and biomechanical analysis. But the inner lives of extinct animals, their thoughts and experiences, remain forever beyond direct observation. Yet even here, science provides tools. By studying modern animals, we learn principles of how brains generate minds. By examining fossil brains and related structures, we constrain possibilities. We won't achieve certainty, but we can make increasingly informed inferences. The revolution in dinosaur intelligence isn't about proving they were geniuses. It's about recognizing they were real animals with real capabilities, not the sluggish monsters of outdated imagination. Every discovery refines understanding. Every fossil adds detail to the picture. The dinosaurs we're discussing lived millions of years ago, but their cognitive abilities are assessed using tools developed for animals alive today. That creates an interesting methodological challenge. How do you measure intelligence in creatures you can never observe behaving? The answer lies in comparative anatomy and functional morphology. Scientists examine brain structures in modern animals, correlate those structures with specific behaviors and capabilities, then look for analogous structures in fossils. It's indirect, yes, but it's grounded in observable relationships. Take the Wulst structure in bird brains. This region handles complex visual processing and spatial reasoning. Larger, more developed Wulsts correlate with enhanced cognitive abilities in living birds. Ravens and parrots, both known for problem-solving skills, have prominent Wulsts. Chickens and pigeons, less cognitively flexible, have smaller ones. When paleontologists find evidence of Wulst-like structures in theropod endocasts, they're not guessing. They're applying established correlations. Same principle applies to the optic lobes, cerebellum, and olfactory bulbs. Each structure has known functions in living animals. Size and organization provide clues about capabilities. A dinosaur with massive optic lobes likely relied heavily on vision. One with an enlarged cerebellum probably had sophisticated motor control. These aren't wild speculations, they're evidence-based inferences. But there's a trap here. Bigger doesn't always mean better. Brain size matters, but organization matters more. A large brain dedicated mostly to processing smell won't necessarily produce complex cognition. What matters is the allocation of neural resources. Are regions associated with higher order processing well developed? Do structures show evidence of specialization? The brain's architecture reveals priorities. Consider crocodiles. They have relatively small brains compared to body size, yet they're capable of surprising behavioral complexity. They cooperate in hunting, communicate with sophisticated vocalizations, and show individual personality differences. Brain size alone would underestimate their capabilities. The same caution applies to dinosaurs. We can't assume a small brain meant simple behavior. The question becomes, what did that brain emphasize? What tasks consumed neural processing power? For predatory theropods, the answer seems clear. Vision, coordination, and likely some degree of strategic thinking. These animals hunted prey that could fight back or flee. Success required more than instinct. For large herbivores, different priorities emerge. Social coordination, spatial memory for food sources, and threat assessment. A triceratops didn't need to plan ambushes, but it needed to recognize predators, coordinate defensive behavior with herdmates, and remember landscape features. Different intelligence, not lesser intelligence. Here's where fossil evidence gets really interesting. Bone pathologies, injuries that healed, tell stories about behavior. A Tyrannosaurus with a healed broken rib survived weeks or months unable to hunt effectively. How? Possibly by scavenging, but more intriguingly, perhaps through social tolerance. If other tyrannosaurs allowed an injured individual to feed from their kills, that suggests complex social dynamics. Recognition of individuals, maintenance of relationships, maybe even something resembling compassion. We see similar patterns in herbivore fossils. Individuals with severe injuries that survived long enough for bones to heal. In solitary animals, such injuries would be death sentences. In social groups, injured individuals can benefit from collective protection and shared resources. The fossil record hints at these dynamics. Trackways showing multiple individuals moving together, bone beds with mixed age classes, suggesting family groups. These aren't proof of intelligence, but they're evidence of behavioral complexity that requires cognitive capabilities. Social behavior demands communication, and we know dinosaurs communicated. Hadrosaurs had elaborate nasal crests that functioned as resonating chambers. They could produce distinctive calls, likely for identification and coordination. Predators probably vocalized too. Modern crocodiles use a range of vocalizations despite their relatively simple brains. Dinosaurs, with more complex brains and social behaviors, almost certainly had richer vocal repertoires. Some dinosaurs may have used visual displays. Crests, frills, and other ornamentation could have served display functions. Changing colors through blood flow or feather erection, similar to modern birds and reptiles. Communication doesn't require high intelligence, but complex communication supports sophisticated social behavior, which does correlate with cognitive development. Here's a question worth considering. Did any dinosaurs have culture? Culture, in the biological sense, means learned behaviors transmitted between individuals and across generations. Tool use techniques in chimpanzees, hunting strategies in orcas, song dialects in whales. These are cultural phenomena. They're not genetically encoded. They're taught, learned, and preserved through social transmission. Could dinosaurs have had culture? It's not impossible. Modern birds demonstrate cultural learning. Japanese crows drop nuts on roads and wait for cars to crack them. That behavior spreads through observation and imitation, not instinct. If some dinosaurs had comparable cognitive capabilities and lived in stable social groups, cultural transmission becomes plausible. We'd never find direct evidence. Culture leaves no fossils unless it involves durable modifications to objects, and even then, recognizing intentional modification in prehistoric contexts is extraordinarily difficult. But absence of evidence isn't evidence of absence. The cognitive toolkit required for culture, observational learning, behavioral flexibility, and social transmission may have existed in some dinosaur species, particularly the larger-brained theropods and perhaps some of the social herbivores. Let's shift focus slightly. Intelligence isn't just about brains. It's about how organisms interact with their environment. Behavioral ecology examines how animals solve problems posed by their environment and social context. Dinosaurs faced complex ecological challenges. How did they respond? Nesting behavior provides fascinating insights. Some dinosaurs built elaborate nests, arranged vegetation in specific patterns, and showed evidence of parental care. That's not automatic behavior. It requires assessment of environmental conditions, selection of appropriate materials, and construction following some internal template. Modern birds building nests aren't consciously designing architecture, but they're making decisions, choosing locations, evaluating materials, responding to failures. Dinosaur nesting sites show similar decision-making. Nests positioned for drainage and temperature regulation. Eggs arranged in careful patterns. Multiple nesting attempts after failures. These aren't signs of genius, but they're evidence of behavioral flexibility and problem-solving. Migration presents another cognitive challenge. Many dinosaurs migrated seasonally. We know this from fossil distributions showing species appearing in high-latitude sites only during certain seasons. Migration requires navigation, the ability to orient using environmental cues, and maintain direction over long distances. Modern animals use various strategies: solar and magnetic orientation, landmark recognition, inherited migratory routes. Even simple navigation requires processing environmental information and making directional decisions. Long-distance migration, covering hundreds or thousands of kilometers, demands sustained goal-directed behavior. You can't migrate by accident. Some dinosaur migrations cross diverse terrain, requiring adaptation to changing conditions, forests to plains to river valleys. Each environment poses different challenges and opportunities. Successfully navigating such journeys suggests considerable behavioral sophistication. What about memory? That's fundamental to many cognitive abilities. Spatial memory for food sources, social memory for individual recognition, episodic memory for past events. Modern reptiles demonstrate spatial memory. Turtles return to natal beaches decades after leaving. That requires retaining and retrieving spatial information over long time frames. Birds show extraordinary memory capabilities. Clark's nutcrackers cache thousands of seeds and remember locations months later. That's not just memory, it's spatial mapping at remarkable scale. Did dinosaurs have comparable memory systems? The brain structures associated with memory in modern animals, the hippocampus in mammals, analogous structures in birds and reptiles, appear in some form in dinosaur endocasts. That suggests memory capabilities, though determining sophistication from fossils remains challenging. But consider what successful dinosaur behavior required. A predator needs to remember territory boundaries, locations of prey concentrations, and characteristics of individual prey animals. A herbivore benefits from remembering food source locations, water sources, and predator encounter sites. These aren't trivial memory demands. They require encoding, storing, and retrieving spatial and temporal information. Here's something that doesn't get discussed enough: play behavior. Young animals in many species engage in play behavior that serves no immediate survival function, but helps develop skills and social bonds. Mammals play, birds play. Even some reptiles show play-like behavior. Did young dinosaurs play? We can't observe behavior in extinct animals, but we can look for anatomical and ecological correlates. Play is most common in species with extended parental care, complex social structures, and big brains relative to body size. Some dinosaurs fit all three criteria. Juveniles of social species protected by adults and not immediately facing survival pressures, would have time for play. And if play occurred, it suggests cognitive development through learning and social interaction. Fossil trackways occasionally show clusters of juvenile prints near adult prints, suggesting supervised activity. That's not proof of play, but it's consistent with the social dynamics that facilitate play behavior. Scratched surfaces near nesting sites might represent juvenile activity. Though distinguishing play from other behaviors in fossil context is essentially impossible, still, the possibility is intriguing. Play requires imagination, the ability to engage in behavior disconnected from immediate survival needs. It's practice for future challenges. If dinosaurs played, they weren't just reacting to stimuli, they were engaging with their world in flexible, exploratory ways. Let's address a persistent question. Were dinosaurs self-aware? Did they possess consciousness in the way mammals or birds do? That's where science reaches its limits. Consciousness is subjective experience. We can't measure it directly, even in living animals. We infer it based on behavior, neural complexity, and evolutionary relationships. Humans are conscious, obviously. Other primates almost certainly are. The evidence for consciousness extends through mammals, probably into birds, possibly into some reptiles. But defining consciousness is notoriously difficult, and testing for it even harder. The mirror test, where animals demonstrate self-recognition, is often used as a consciousness marker. Great apes, dolphins, elephants, and magpies pass. Most animals don't. Does that mean they're not conscious? Not necessarily. The test may measure specific cognitive abilities rather than consciousness itself. Dinosaurs can't take mirror tests. We're left with indirect assessment. Did they show evidence of complex subjective experience? The neural substrate for consciousness, whatever that is, requires certain brain structures. Dinosaurs had brains. Some had quite complex brains. Whether that complexity crossed whatever threshold generates consciousness remains unknown. Perhaps that's okay. Perhaps the question itself is flawed. Consciousness likely isn't binary, present or absent. It's probably a spectrum. Simple organisms have simple experiences. Complex organisms have richer experiences. Dinosaurs fell somewhere on that spectrum, varying by species and individual. A troodon probably experienced the world more richly than an ankylosaurus, based on brain complexity. But both experienced something. They weren't biological robots. They perceived, processed, and responded. That's experience, even if we can't characterize its subjective nature. What we can say is this: dinosaurs were cognitively diverse, behaviorally flexible, and ecologically successful for over 160 million years. That success required solving problems, adapting to changes, and competing with other species. Simple, inflexible organisms don't dominate ecosystems for geological timescales. The more we learn about dinosaur brains, the more impressed we should be. Not because they were secretly brilliant, but because they were competent. They did what they needed to do, and they did it well. Different species evolve different cognitive strategies suited to their ecological niches. No single approach defined dinosaur intelligence. Evolution doesn't produce general intelligence as a goal. It produces solutions to specific problems. Dinosaurs evolved the cognitive capabilities their lifestyles demanded. Sometimes that meant sophisticated vision and motor control. Sometimes it meant social coordination and communication. Sometimes it meant memory and spatial reasoning. Each species represents a different experiment in how to build a successful animal. Here's the part that genuinely surprises people. Some dinosaurs were probably smarter than many modern animals. A troodon might have outperformed a chicken or a turtle in problem-solving tasks. We'll never know for certain, but the anatomical evidence suggests it's plausible. That doesn't make troodon a genius. It makes it a competent predator with cognitive abilities appropriate to its lifestyle. The comparison isn't about ranking intelligence. It's about recognizing that cognitive evolution doesn't follow a linear progression. Different lineages develop different capabilities. Some dinosaurs were cognitively sophisticated, others weren't. Just like modern animals. The real revolution is abandoning the assumption that extinct means stupid. Old reconstructions portrayed dinosaurs as dim-witted, sluggish, and primitive. Every piece of evidence contradicts that view. They were active, responsive, and behaviorally complex. Some were intelligent by any reasonable definition. They weren't prehistoric philosophers, but they weren't mindless eating machines either. They were animals, real animals with real capabilities. And that's far more interesting than either extreme caricature. Understanding how dinosaurs thought requires looking at what they actually did. Behavior leaves traces. Not always obvious traces, not always interpretable traces, but traces nonetheless. Fossilized footprints, nesting sites, bone beds, stomach contents. Each one tells part of the story. Together they reveal animals that weren't just reacting to stimuli, but engaging with their environment in surprisingly sophisticated ways. Start with nesting behavior. Multiple dinosaur species built nests, not random piles of dirt, but structured arrangements. Maiasaura, the good mother lizard, created bowl-shaped nests in colonial groups. Dozens of nests clustered together, spaced precisely far enough apart that adults wouldn't step on neighboring eggs. That's spatial planning. That's social coordination. These weren't solitary animals randomly depositing eggs. They were selecting nest sites, constructing specific structures, and doing so in organized groups. The nests themselves show attention to detail. Some species lined nests with vegetation. Why? Probably for temperature regulation. Rotting plants generate heat, helping incubate eggs. That's tool use. Simple tool use, but tool use nonetheless. Recognizing that vegetation produces heat, collecting it, arranging it purposefully, that requires connecting cause and effect across time. Plant today, warmth tomorrow. Not all animals manage that cognitive leap. Fossilized embryos inside eggs reveal even more. Some species show evidence of extended incubation periods, suggesting parental care. You don't sit on eggs for weeks or months without behavioral commitment. Crocodiles guard nests. Birds incubate eggs. Both are dinosaur relatives. The behavior likely extends back to dinosaurs themselves. Oviraptor was literally named egg thief because the first specimen was found on a nest, presumed to be stealing eggs. Turns out it was protecting its own nest. Sitting on eggs, guarding them from predators. That's parental investment. That's planning for the future. That requires valuing something that doesn't exist yet, offspring that haven't hatched. Then there's evidence of post-hatching care. Maiasaura nests contain remains of hatchlings at different growth stages. The young stayed in or near nests after hatching. Adults brought food. This isn't speculation. The fossil evidence shows it. Hatchling bones, worn teeth, trampled nest edges. Young animals don't survive weeks in nests without provisioning. Parents fed them. That's extended parental care, something relatively rare in reptiles but common in birds. Dinosaurs bridge that gap. Some species apparently invested heavily in offspring survival. That investment requires memory, planning, and sustained behavioral commitment. You can't accidentally care for young over weeks or months. Trackways provide another window into behavior. Not individual footprints, but sequences. Paths showing where animals walked, how fast, whether they traveled alone or in groups. Sauropod trackways often show multiple individuals moving together. Adults and juveniles. Different sizes, same direction, same time. That's herding. That's social structure. You don't accidentally walk alongside dozens of other animals for miles. That requires group cohesion, probably communication, possibly coordination. Were they protecting young? Sharing information about food or water? We can't know specifics, but the behavior itself is clear. They traveled in groups, and groups require social cognition. Predator trackways tell different stories. Some show stalking patterns, approaches from downwind, curved paths suggesting ambush positions. One famous trackway shows multiple theropods apparently coordinating an approach on a sauropod herd. Did they hunt cooperatively? The evidence is circumstantial but suggestive. Modern pack hunters show similar approach patterns. Coordinated hunting requires communication, role differentiation, and shared goals. That's cognitively demanding. Not every predator manages it. Wolves do. Lions do. Komodo dragons don't. Where did dinosaurs fall? Probably varied by species. But some apparently hunted in ways suggesting coordination. Bone beds offer another clue. Mass accumulations of single species. Dozens or hundreds of individuals dying together. Why? Sometimes catastrophic events like floods, but other times seasonal aggregations. Animals gathering at specific locations, specific times. That requires memory of place, timing, and purpose. Salmon return to spawning grounds. Wildebeest migrate on schedule. Both require internal maps and calendars. Some dinosaurs apparently had both. Ceratopsian bone beds suggest seasonal gatherings, possibly for breeding or resource access. That's planned behavior based on environmental cues and memory. Stomach contents and coprolites, fossilized feces, reveal dietary choices. Some dinosaurs were generalists, eating whatever was available. Others were specialists, targeting specific plants or prey. Specialization requires recognition, selection, and sometimes preparation. Herbivores often show evidence of selective feeding, preferring certain plant types over others. That's discrimination. That's choice. Not every animal bothers choosing food beyond edible versus inedible. Choosy eaters need memory of which foods taste better, provide more nutrition, or cause less digestive trouble. They need ability to recognize preferred foods among alternatives. That's cognitive filtering. Pathologies, injuries, and diseases preserved in bone tell stories about survival. Many dinosaurs lived with healed fractures, infections, or disabilities. A T-Rex named Sue had numerous healed injuries, including broken ribs and infected jaw. She survived all of them, lived to old age. How? Healing takes time. Injured animals are vulnerable. They can't hunt or flee effectively. Yet many dinosaurs survived serious injuries. That suggests either remarkable toughness, social support, or both. Could injured individuals have received help from group members? Possible. Speculative, but possible. Elephants and dolphins both assist injured companions. If some dinosaurs were highly social, similar behavior isn't absurd. Bone modifications from feeding provide insight into problem solving. Some fossils show tool marks, places where teeth scraped bone in specific patterns. Predators weren't just biting randomly. They were targeting joints, separating limbs, accessing marrow. That requires anatomical understanding, knowing where bones connect, how they come apart, which parts are worth the effort. Modern predators learn these skills. Wolves know how to disassemble prey efficiently. Dinosaurs apparently did too. That's learned behavior, probably culturally transmitted from adults to young. Tooth marks on bones sometimes show interesting patterns. Bite marks clustered around specific areas. Avoided areas. Preferential targeting of nutritious parts. That's selective consumption. That's decision-making. Not just eating everything available, but choosing what to eat, what to leave, what's worth the effort. That requires evaluating options and making choices. Simple organisms don't bother. They eat until full or until food is gone. Selective feeders need more sophisticated behavioral control. Gastroliths, stomach stones, appear in some dinosaur species. Sauropods swallowed rocks to aid digestion, grinding plant material in muscular stomachs. Birds do this. Crocodiles do this. It's a solution to a specific problem: how to break down tough plant material without good chewing teeth. Recognizing that swallowing rocks helps digestion requires connecting actions with delayed internal consequences. You don't immediately feel digestion improving. The benefit comes hours later. That's a cognitively challenging connection to make. Yet multiple dinosaur lineages figured it out. Trace fossils occasionally preserve moments of behavior frozen in time. A predator footprint inside a herbivore footprint. An attack in progress. A swimming dinosaur paddling with forelimbs. A resting trace, where an animal settled down and left a body impression. Each one captures a second of life, a decision made, an action taken. Together they build a picture of animals navigating complex lives. Not every moment was about survival. Some traces show play behavior, young animals running in circles, leaving chaotic trackways. Play is cognitively significant. It's practice for adult behaviors, but it's also evidence of behavioral flexibility, curiosity, and energy surplus. Only animals with comfortable lives can afford play. Dinosaur social structures probably varied enormously. Some species were likely solitary except for breeding. Others lived in bonded pairs. Still others formed large herds or packs. Each social structure demands different cognitive skills. Solitary animals need self-sufficiency, environmental knowledge, and independence. Social animals need communication, cooperation, and conflict resolution. Herd animals need coordination and conformity. Pack hunters need role differentiation and strategic thinking. We see evidence for all these social structures among different dinosaur groups. That means cognitive diversity, different species solving social challenges in different ways. Communication was certainly present. Exactly how dinosaurs communicated remains partially mysterious, but they definitely communicated. Hadrosaurs had elaborate crests, hollow structures connected to nasal passages, sound resonance chambers. They could produce low-frequency calls, possibly for long-distance communication. Different species had different crest shapes, probably producing different sounds. That's acoustic diversity. That's potential for complex vocal communication. Could they have had something resembling language? Almost certainly not language as we define it, but structured calls with specific meanings. That's plausible. Many animals manage that. Vervet monkeys have different alarm calls for different predators. Prairie dogs have calls that describe predator type, size, and color. Why not dinosaurs? Visual communication was probably important too. Many dinosaurs had elaborate ornamentation. Frills, horns, crests, plates, spikes. Some were defensive, but many were display structures. Bright colors, distinctive patterns, sexual dimorphism, all suggest visual signaling. Animals showing off need audiences capable of appreciating displays. That requires visual processing, pattern recognition, and aesthetic judgment, if we can call it that. Choosing mates based on display quality means evaluating displays, comparing options, making decisions. That's social cognition. That's discrimination based on multiple factors. Chemical communication probably existed, but leaves no fossil evidence. Modern reptiles use chemical signals extensively. Pheromones, scent marking, chemical tracking. Dinosaurs likely did too. Olfactory bulbs in dinosaur brains suggest strong sense of smell in many species. Smell is cognitively interesting because it requires memory. Recognizing a scent means remembering previous encounters with that scent. Associating smells with specific individuals, locations, or situations requires building mental libraries of olfactory information. That's memory-dependent cognition. Territorial behavior probably existed in many species. Territories require memory of boundaries, recognition of intruders, and defense strategies. Modern animals mark territories, patrol boundaries, and confront trespassers. Dinosaurs probably did similarly. Evidence is indirect but reasonable. Concentrated fossil distributions sometimes suggest range fidelity, Animals staying in specific areas over time. Repeated use of the same nesting sites across years. That's site fidelity. That's memory of place. That's territorial behavior. Migration is another complex behavior some dinosaurs might have exhibited. Following seasonal resources requires environmental knowledge, timing, and navigation. Modern animals migrate using various cues, sun position, magnetic fields, landmarks, even smell. Which cues dinosaurs used, if they migrated at all, remains unknown. But some fossil distributions suggest seasonal movements. Different species appearing in different layers corresponding to different seasons. That's circumstantial, but intriguing. Migration is cognitively demanding. It requires knowing where to go, when to go, and how to get there. Animals don't accidentally migrate successfully. Problem-solving ability is hard to assess in extinct animals, but we can make educated guesses. Animals that faced variable environments needed behavioral flexibility. Dinosaurs lived through climate changes, habitat shifts, and ecological disruptions. Species that survived needed adaptability. Rigid behavioral programs work fine in stable environments. Changing environments demand flexibility, learning, and innovation. Dinosaurs persisted for 160 million years through multiple extinction events and climate fluctuations. That's evidence of adaptability. Not necessarily individual problem-solving, but certainly lineage-level behavioral flexibility. Tool use might have existed in limited forms. We've discussed gastroliths, stomach stones as digestive tools. Some theropods might have used objects to crack eggs or access food. Evidence is absent, but absence of evidence isn't evidence of absence. Fossilization rarely preserves tool use. Modern birds use tools extensively. Crows fashion hooks from wire. Parrots use sticks to scratch themselves. Herons use bait to attract fish. Dinosaurs were ancestral to birds. Tool use probably appeared somewhere in that lineage. Whether non-avian dinosaurs used tools remains unknown. But it's not ridiculous speculation. Learning was definitely present. All animals learn. The question is how much and what types. Dinosaurs certainly learned through experience. Predators learned hunting techniques. Herbivores learned which plants were nutritious or toxic. Social species learned group dynamics. Young learned from adults. That's cultural transmission, behavior passed not through genes but through observation and teaching. Modern animals show extensive cultural learning. Elephants teach young where water sources are. Orcas teach hunting techniques specific to their pods. Chimpanzees have regional tool use cultures. Did dinosaurs have cultures? Impossible to prove. But they probably had learned traditions. Behavioral variations passed through generations within populations. Play behavior deserves another look. Young animals play. That's nearly universal among vertebrates. Play serves multiple functions. Practicing adult behaviors, building physical skills, establishing social bonds, exploring environments safely. Fossil evidence of play is extraordinarily rare because play doesn't usually leave traces. But trackways occasionally show patterns consistent with play. Chaotic running patterns, circular paths, multiple juveniles moving together without apparent purpose. That looks like play. If dinosaurs played, that's significant. Play requires energy surplus, safety, and curiosity. It's evidence of childhood, extended development periods where young animals aren't just surviving, but learning, exploring, and developing. Emotional capacity is even harder to assess than intelligence. But emotions aren't mysterious magic. They're neurological states driving behavior. Fear motivates escape. Aggression motivates defense. Curiosity motivates exploration. Pleasure reinforces beneficial behaviors. All vertebrates show emotional responses. Dinosaurs certainly experienced emotions. The question is which emotions and how complex. Did they feel affection, grief, jealousy. We'll never know subjective experiences. But behavioral evidence suggests at least basic emotions. Parental care suggests bonding. Social living suggests group cohesion and probably conflict. Mating displays suggest mate preference, perhaps even something resembling attraction. Here's what we can say confidently. Dinosaurs weren't simple. They weren't uniform. They weren't primitive. They were diverse animals with diverse behaviors, diverse cognitive abilities, and diverse ways of engaging with their worlds. Some were probably quite intelligent, others less so. Just like modern animals, the spectrum of dinosaur cognition likely matched or exceeded the spectrum we see in modern reptiles and birds. That's a wide spectrum, from relatively simple to genuinely impressive. The revolution in understanding dinosaur intelligence isn't claiming they were geniuses. It's recognizing they were competent, capable, and far more sophisticated than previously imagined. They built nests, raised young, communicated, cooperated, migrated, and solved problems. They lived complex lives in complex environments. That required brains capable of managing complexity. And that's exactly what the fossil evidence increasingly shows. Intelligence is one dimension of cognition. Memory is another, and it's equally fascinating. Modern animals demonstrate memory capacities ranging from seconds to decades. Goldfish, despite the myth, remember for months. Elephants remember herd members and watering holes for over 50 years. Where did dinosaurs fall on this spectrum? Memory leaves no fossils, but behavior demands it. Migration requires remembering routes across thousands of miles. Nesting requires remembering nest sites, sometimes returning to the same location year after year. Social recognition requires remembering individuals, their relationships, their hierarchies. All of this points to sophisticated memory systems. Hadrosaurs migrating between breeding and feeding grounds needed spatial memory. Remembering landmarks, terrain features, seasonal changes. That's not simple. Modern migratory birds possess remarkable navigational memory, encoding magnetic fields, star patterns, and geographic features. Dinosaurs likely used similar systems. Their brains had the necessary structures. The flocculus, a region associated with spatial processing and navigation, was well developed in many species. Parental care also demands memory. Recognizing your own offspring among dozens or hundreds of juveniles requires individual recognition and memory retention. Modern crocodiles recognize their young by sound and scent for months. Birds recognize offspring visually and acoustically. Dinosaurs nesting in colonies, surrounded by other families, needed comparable abilities. Otherwise, parental investment would be wasted on unrelated young. That didn't happen. Fossil evidence shows parents focused care on specific nests, specific juveniles. Memory made that possible. Social memory becomes even more complex. Living in groups means tracking relationships. Who's dominant? Who's subordinate? Who's trustworthy? Who's aggressive? Maintaining stable hierarchies requires remembering past interactions. Modern social animals, from wolves to primates, maintain detailed social maps in their minds. Dinosaurs living in herds probably did the same. Ceratopsians with complex frill displays likely remembered which individuals displayed dominance. Theropods hunting in groups probably remembered which pack members were reliable during hunts. This isn't speculation without foundation. Brain endocasts show well-developed temporal lobes in many dinosaur species. Temporal lobes handle memory formation and retrieval. Their presence suggests memory capacity beyond basic reflexes. Learning and memory are inseparable. You can't learn without remembering what you learned. Every predator improving hunting techniques, every herbivore avoiding toxic plants, every juvenile watching adults. All of that required memory encoding and retrieval. Consider tyrannosaurs again. A young Tyrannosaurus learning to hunt didn't master the skill instantly. It required practice, failure, adjustment, and improvement. That's learning. But it also required remembering what worked and what didn't. Memory consolidated those lessons. Without memory, every hunt would be the first hunt. That's not how predators work. Experience accumulates, skills develop, memory enables that development. Dinosaurs also likely possessed episodic-like memory, the ability to remember specific events. Modern birds demonstrate this capacity. Scrub jays remember where they cached food, what type of food, and how long ago. That's remembering what, where, and when. It's sophisticated. Did dinosaurs possess similar abilities? Probably some did. Troodontids, with their large brains and complex behaviors, were good candidates. Oviraptorosaurs brooding nests in specific locations, returning seasonally, might have remembered previous nesting attempts. Success or failure would inform future decisions. That requires remembering specific past events, not just generalized knowledge. Long-term memory also played a role in survival. Remembering drought locations, predator territories, and seasonal food availability would provide significant advantages. Herbivores returning to productive feeding areas year after year weren't wandering randomly. They remembered. Predators avoiding well-defended prey or targeting vulnerable individuals weren't acting on instinct alone. They remembered outcomes. Here's where it gets interesting. Memory isn't just storage, it's reconstruction. Every time you remember something, your brain rebuilds that memory, sometimes altering it slightly. Modern animals show memory flexibility. Rats navigating mazes adjust their mental maps when layouts change. Dolphins remember signature whistles of individuals they haven't encountered in decades, then recognize them immediately upon reunion. Dinosaur memory systems probably shared these features. Flexible, adaptive, and capable of long-term retention. The fossil record hints at this through behavioral consistency. Trackways showing repeated use of the same paths. Nesting grounds used across multiple generations. Migration routes maintained over evolutionary timescales. All of this implies memory, both individual and possibly cultural. If adults taught juveniles migration routes, that's cultural memory transmission. Information passed not genetically, but behaviorally. Modern elephants do this. Matriarchs lead herds to water sources their grandmothers showed them. Dinosaurs might have done the same. Sensory memory also matters. Animals remember smells, sounds, and sights associated with danger or reward. A hadrosaur encountering a tyrannosaur would remember that experience. Next time, the scent or sound of a large predator would trigger avoidance. That's sensory-linked memory. It's automatic, fast, and essential for survival. Modern prey animals demonstrate this constantly. Zebras remember lion roars. Gazelles remember cheetah profiles. Dinosaurs weren't different. Their survival depended on recognizing threats quickly. Memory made that possible. Emotional memory adds another layer. Events tied to strong emotions, fear, pain, pleasure, are remembered more vividly. This is universal across vertebrates. A dinosaur surviving a predator attack would remember that event intensely. The location, the circumstances, the sensations. That memory would shape future behavior, increasing vigilance in similar situations. Modern animals show this clearly. A dog attacked by another dog remembers and avoids similar dogs. A bird escaping a predator remembers and avoids that area. Dinosaurs experience the same memory-emotion link. Their brains had the limbic structures necessary for emotional memory encoding. Fear conditioning, reward association, all of that was present. Sleep likely played a role in memory consolidation, just as it does in modern animals. Sleep isn't just rest. It's when brains process experiences, strengthening important memories, and discarding irrelevant information. Modern reptiles and birds sleep, and their brains show activity patterns consistent with memory processing. Dinosaurs almost certainly slept, and their brains almost certainly used that time for memory consolidation. Without that process, learning would be inefficient. Memories would fade quickly, skills wouldn't develop. Sleep made memory durable. Forgetting is also important. Not everything needs remembering. Brains that remember everything become cluttered, inefficient. Modern animals forget irrelevant details while retaining important information. Dinosaurs probably did the same. A hadrosaur didn't need to remember every plant it ate, but it needed to remember which plants caused illness. Selective memory, prioritizing survival-relevant information, would be advantageous. The evolution of memory in dinosaurs likely paralleled their ecological complexity. Early dinosaurs in simpler environments probably had simpler memory systems. Later species in complex ecosystems, dealing with social dynamics, migration, and diverse threats, needed more sophisticated memory. That's reflected in brain evolution. Later species show larger, more complex brains with enhanced regions associated with memory and learning. Theropod. Memory likely varied by lifestyle. Solitary hunters needed different memory skills than pack hunters. A lone Allosaurus needed spatial memory for territory and prey locations. A pack-hunting Deinonychus needed social memory for coordinating with group members. Both required memory, but different types emphasized different capacities. Herbivore memory probably focused on resource distribution and predator avoidance. Remembering seasonal plant availability, water sources, and safe migration routes would be critical. Large sauropods traveling vast distances needed exceptional spatial memory. Their tiny brains relative to body size seem paradox, but brain size isn't everything. Efficiency matters. Sauropod brains might have been optimized for essential functions, including long-term spatial memory, without unnecessary elaboration. Avian dinosaurs, the ancestors of modern birds, clearly possessed advanced memory. Modern birds demonstrate remarkable capacities. Chickadees remember thousands of food cache locations. Pigeons navigate using memorized landmarks. Parrots remember human faces and voices for years. These abilities didn't appear suddenly. They evolved gradually in the theropod lineage. Non-avian theropods probably possessed proto-versions of these capacities. Archaeopteryx, perched between non-avian dinosaurs and modern birds, likely had memory systems more advanced than earlier theropods, but less refined than modern birds. It's a transitional form in cognition as well as anatomy. Memory also connects to problem solving. Solving problems requires remembering previous attempts. A dinosaur figuring out how to access difficult food needed to remember what didn't work. Trial and error learning depends entirely on memory. Without memory, every trial is independent, and learning never occurs. Dinosaurs clearly learned, so they clearly remembered. The interplay between memory and intelligence is seamless. You can't separate them. Intelligent behavior requires remembering past experiences and applying that knowledge to new situations. Dinosaurs demonstrating problem-solving, learning, and behavioral flexibility were demonstrating memory capacity simultaneously. One implies the other. Fossil evidence occasionally provides indirect memory clues. Healed injuries show individuals survived trauma and adjusted behavior to avoid repeat incidents. That's memory influencing future actions. Dinosaurs with multiple healed wounds were learning from experience, remembering danger and adapting. Trackways showing individuals returning to the same locations repeatedly, nesting sites used across seasons, all suggest memory-guiding behavior. These aren't definitive proofs, but they're consistent with sophisticated memory systems. Comparative anatomy strengthens the case. Dinosaur brain structures resemble those of modern animals with known memory capacities. The hippocampus, critical for spatial memory in mammals and birds, has analogues in reptilian brains. Dinosaurs possessed these structures. Their function was probably similar. Spatial memory, navigational memory, and contextual memory were likely present. The revolution in understanding D. Dinosaur cognition includes recognizing memory as a core component. Dinosaurs weren't just reacting to immediate stimuli. They were drawing on past experiences, anticipating future events, and adjusting behavior accordingly. That's sophisticated. It's not human-level cognition, but it's far beyond robotic stimulus response. Memory made dinosaurs competent, capable, and successful for over 160 million years. Their ability to remember, learn, and adapt was fundamental to their dominance. Modern animals show us what's possible. Elephants mourning dead relatives, whales singing songs passed through generations, crows holding grudges against specific humans for years. These behaviors all depend on memory. Dinosaurs weren't elephants or whales or crows, but they were complex animals navigating complex worlds. Memory was essential. Without it, survival would be impossible. With it, dinosaurs thrived. They remembered where to nest, how to hunt, whom to trust, and what to fear. Memory shaped their lives as profoundly as their anatomy. And that memory, encoded in neural structures we can partially reconstruct, tells us dinosaurs were far more cognitively sophisticated than once believed. They weren't simple. They weren't primitive. They were remembering, learning, adapting creatures whose mental lives, while unknowable in detail, were undoubtedly rich and complex. The social dimension of dinosaur intelligence deserves closer attention. Intelligence doesn't exist in isolation. It evolves in response to environmental pressures, and one of the most powerful pressures is social complexity. Living in groups creates cognitive demands that solitary life doesn't. You need to recognize individuals, track relationships, remember past interactions, predict behavior, cooperate, compete, deceive, and reconcile. Social animals develop larger brains relative to body size. The correlation is consistent across mammals, birds, and even fish. Dinosaurs were no exception. Evidence for social behavior in dinosaurs is substantial. Trackways show groups traveling together, adults and juveniles moving in coordinated herds. Bone beds contain multiple individuals of the same species, often different age classes, suggesting they lived together and died together. Nesting sites reveal colonial breeding, with dozens of nests clustered in close proximity. These aren't random aggregations. They're deliberate social structures. Hadrosaurs provide compelling examples. Maiasaura nested in colonies. Fossil sites in Montana reveal dozens of nests spaced evenly, indicating social coordination. Adults return to the same sites annually, a behavior requiring memory and social tradition. Hatchlings stayed in nests while adults provided care, a level of parental investment that implies complex social bonds. Raising young together requires communication, cooperation, and probably social hierarchies determining nest placement and resource access. Ceratopsians also lived socially. Massive bone beds of Centrosaurus contained thousands of individuals spanning all age groups. These weren't mass death events from predation. They were herds crossing rivers during migration, possibly drowning during floods. The sheer number suggests sophisticated herd dynamics. Maintaining group cohesion across such large populations requires communication systems, leadership structures, and individual recognition. You can't coordinate thousands of animals without cognitive complexity. Theropods weren't exempt from social pressures either. Tyrannosaurs likely hunted in family groups. Fossil sites show multiple individuals of different ages together, and biomechanical studies suggest coordinated hunting strategies. Younger tyrannosaurs were faster, older ones more powerful. Hunting cooperatively exploits these differences. Cooperation requires planning, communication, and probably some division of labor. That's cognitively demanding. Deinonychus, the raptor made famous by popular culture, also shows evidence of pack behavior. A bone bed in Montana contains several Deinonychus individuals alongside a single Tenontosaurus, a much larger herbivore. The interpretation, though debated, suggests coordinated group hunting. Taking down prey significantly larger than yourself requires teamwork. Individuals need roles, timing, and communication. Pack hunting is one of the most cognitively complex behaviors in the animal kingdom. Social intelligence manifests differently than solitary intelligence. Solitary animals focus on environmental problem solving, spatial navigation, and resource acquisition. Social animals add layers. They navigate social landscapes as complex as physical ones. Who's dominant? Who's trustworthy? Who owes whom a favor? These questions demand memory, theory of mind, and strategic thinking. Dinosaurs living in groups face these questions daily. Theory of mind is the ability to understand that others have thoughts, intentions, and perspectives different from your own. It's rare. Most animals lack it. Humans have it fully developed. Great apes show rudimentary versions. Some birds, particularly corvids, demonstrate surprising abilities. Whether dinosaurs possess theory of mind is speculative, but social complexity suggests at least proto-versions existed. Deception, a behavior requiring theory of mind, may have occurred. An individual pretending not to notice food to return later when others leave. A subordinate feigning injury to avoid conflict. These are hypothetical, but plausible. Communication is inseparable from social intelligence. Dinosaurs communicated. Vocalizations were common, evidenced by resonating chambers in hadrosaur crests and hollow skull structures in other species. Parasaurolophus crests functioned as musical instruments, producing low-frequency calls that traveled long distances. These weren't random noises. They conveyed information. Calls could signal danger, coordinate movement, establish territory, or attract mates. Complex calls require neural infrastructure for production and interpretation. That infrastructure supports cognitive complexity. Visual signals also mattered. Bright crests, elaborate frills, colorful patterns. These weren't just for show. They communicated status, health, and identity. Reading these signals requires perceptual sophistication and memory. Recognizing individuals by appearance, remembering past interactions, and adjusting behavior accordingly. Social animals do this constantly. Dinosaurs living in groups almost certainly did too. Body language added another layer. Posture, movement, positioning, dominance displays, submission gestures, threat postures. Modern animals use body language extensively. Birds fluff feathers, reptiles inflate throats, mammals bare teeth. Dinosaurs had equivalent behaviors, a ceratopsian lowering its head and displaying its frill, a theropod spreading arms and hissing. These communicated intent and status without physical conflict. Interpreting body language requires observation, memory, and social learning. Young dinosaurs watching adults, learning appropriate responses, internalizing social norms. Play behavior, observed in many intelligent animals, probably occurred in dinosaurs. Play serves crucial developmental functions. It teaches physical skills, social rules, and problem-solving strategies. Mammalian carnivores play extensively. Young lions wrestle, chase, and mock hunt. Birds play with objects, testing their properties. Crocodiles, close dinosaur relatives, engage in play. Young crocodiles chase each other and play with objects in water. Dinosaurs, especially social species, likely played. Juvenile tyrannosaurs mock fighting, hadrosaurs chasing through nesting colonies, young sauropods testing strength by pushing. Play requires cognitive flexibility, imagination, and social awareness. Its presence indicates intelligence. Parental care, evident in multiple dinosaur groups, demands intelligence. Raising offspring isn't automatic. Parents must recognize their young, provide appropriate care, protect against threats, and teach survival skills. Maiasaura adults fed hatchlings in nests. Oviraptors brooded eggs like modern birds. These behaviors require planning, patience, and emotional investment. They're cognitively costly, but evolutionarily valuable. Dinosaurs investing in parental care were investing in cognition. Teaching a rare behavior may have occurred. Teaching requires recognizing another's ignorance and deliberately providing information. Most animals don't teach. Humans do extensively. Some great apes show teaching behaviors. Meerkats teach pups to handle prey. Certain birds demonstrate hunting techniques to fledglings. Did dinosaurs teach? Direct evidence is absent, but the possibility exists. Adult tyrannosaurs bringing wounded prey to juveniles, allowing practice kills. Adult hadrosaurs leading young to feeding grounds, demonstrating edible plants. Speculative, yes, but consistent with observed parental care and social complexity. Empathy, the ability to understand and share another's emotional state, correlates with social complexity. Elephants console distressed herd members. Dolphins support injured companions at the surface. Primates comfort each other after conflicts. Did dinosaurs experience empathy? We'll never know subjectively, but behavioral evidence suggests proto-empathy existed. Parents responding to distressed hatchlings, herd members slowing for injured individuals. These behaviors, observed indirectly through trackways and bone beds, hint at emotional sensitivity. Empathy isn't purely cognitive, but it requires cognitive processing of social and emotional information. Altruism, behavior benefiting others at personal cost, occasionally appears in social animals. It's evolutionarily puzzling, but cognitively fascinating. Helping relatives spreads shared genes. Reciprocal altruism builds alliances. Dinosaurs living in stable social groups had opportunities for both. An adult defending the herd against predators, risking injury, individuals sharing food, or allowing subordinates access to resources. These behaviors require restraint, social awareness, and probably emotional bonds. They indicate cognitive sophistication beyond simple self-interest. Social learning accelerates adaptation. Instead of every individual discovering solutions independently, knowledge spreads through observation and imitation. One dinosaur discovers a new food source. Others watch and learn. A juvenile observes adults escaping predators, internalizes strategies. Social learning creates culture, shared behavioral traditions passed across generations. Evidence for dinosaur culture is indirect but suggestive. Colonial nesting sites used repeatedly across years. Migration routes followed generation after generation. These patterns suggest learner traditions, not just instinct. Culture requires memory, imitation, and social transmission. Young animals must observe, remember, and replicate behaviors. Adults must tolerate observation and sometimes actively demonstrate. This creates cumulative knowledge, each generation building on the last. Human culture is the extreme version, but rudimentary culture exists in many species. Whales have vocal dialects. Chimpanzees have tool use traditions. Crows have regional problem-solving techniques. Dinosaurs, living in stable social groups for millions of years, had time and opportunity for cultural evolution. Conflict resolution is another social cognitive skill. Living together creates friction. Resources are limited. Mates are contested. Hierarchies shift. Social animals need mechanisms to resolve conflicts without constant violence. Dominance displays replace fighting. Submission gestures prevent escalation. Reconciliation repairs relationships after disputes. Modern animals reconcile. Primates groom after fights. Elephants intertwine trunks. Ravens preen former opponents. Dinosaurs almost certainly had equivalent behaviors. A ceratopsian backing down after a display, avoiding combat. A hadrosaur offering a submissive posture, restoring peace. These behaviors require recognizing emotional states, predicting outcomes, and choosing strategies. That's intelligence. Loneliness, experienced by social animals separated from groups, indicates cognitive and emotional bonds. Isolated social animals show stress, altered behavior, and even health decline. Elephants separated from herds become depressed. Parrots pluck feathers when lonely. Social bonds aren't optional for these animals. They're psychological necessities. Dinosaurs living in herds likely experienced similar needs. An isolated hadrosaur, separated during migration, would probably seek the herd actively. Reuniting would trigger observable relief behaviors. These aren't anthropomorphic projections. They're consistent with what we observe in modern social animals. The cognitive demands of social life drove brain evolution in mammals and birds. The social brain hypothesis proposes that intelligence evolved primarily to navigate social complexity, not environmental challenges. Larger social groups correlate with larger brains, particularly in regions handling social information. Dinosaurs living in large, stable groups face these same pressures. Their brains likely adapted accordingly. While we can't measure their social brain regions precisely, the behavioral evidence strongly suggests sophisticated social cognition. Comparing dinosaur social behavior to modern analogues reveals plausible cognitive parallels. Hadrosaur colonies resemble bird colonies with similar spacing, coordination, and communication. Ceratopsian herds mirror ungulate herds, with comparable group dynamics and migration patterns. Tyrannosaur family groups echo wolf packs, with potential role differentiation and cooperative strategies. These aren't perfect comparisons, but they're informative. If modern animals with these behaviors possess certain cognitive abilities, dinosaurs with similar behaviors likely possess similar abilities. Social intelligence and individual intelligence reinforce each other. Smart individuals form more complex societies. Complex societies select for smarter individuals. It's a positive feedback loop. Over millions of years, this loop drove cognitive evolution in multiple dinosaur lineages. The result was animals capable of coordinated group living, sophisticated communication, long-term social bonds, and possibly cultural traditions. These weren't simple creatures. They were socially savvy, emotionally connected, and mentally flexible. The revolution in understanding dinosaur intelligence isn't just about bigger brains or problem solving. It's about recognizing them as complete animals. They had social lives, emotional experiences, memories, and probably individual personalities. Some were bold, others cautious. Some were leaders, others followers. They formed friendships, rivalries, and family bonds. They communicated, cooperated, and occasionally deceived. They lived rich, complex lives shaped by both their environments and their societies. Dinosaurs dominated Earth for over 160 million years. That success wasn't accidental. It required adaptability, learning, memory, and social coordination. Intelligence, in its many forms, was fundamental. Not human intelligence, but dinosaur intelligence. Appropriate for their worlds, their bodies, and their challenges. Understanding this transforms how we view them. They weren't prehistoric monsters or evolutionary dead ends. They were successful, sophisticated animals whose cognitive abilities allowed them to thrive across changing climates, continents, and ecological niches. Modern birds, dinosaurs' living descendants, remind us daily of this legacy. Watch a crow solving a puzzle, a parrot learning words, or a chickadee remembering hundreds of food caches. You're watching dinosaur intelligence in action. The neural architecture, the cognitive flexibility, the social awareness, all inherited from their theropod ancestors. Birds didn't suddenly become smart. They continued a cognitive trajectory that began long before they could fly. The story of dinosaur intelligence is still being written. Every fossil discovery, every biomechanical analysis, every comparative study adds pieces to the puzzle. We'll never know exactly what it felt like to be a triceratops or a velociraptor. Subjective experience is locked in the past. But we can infer, we can compare, and we can reconstruct. The picture emerging is clear. Dinosaurs were cognitively complex, socially sophisticated, and mentally capable. They deserve recognition, not just as successful animals, but as intelligent ones. Their minds, as impressive as their bodies, shaped their evolutionary success and their lasting legacy. And that legacy, carried forward by birds, continues to fly, sing, and think in our modern world. The evidence sits before us like fossils arranged in stone. Dinosaur brains weren't just functional organs managing basic reptilian processes. They were sophisticated neural architectures capable of learning, memory, social coordination, and behavioral flexibility. From the massive herds of hadrosaurs calling to each other across Cretaceous plains to the calculated strategies of pack-hunting theropods, these animals demonstrated cognitive abilities that demand our respect and recognition. We spent over a century getting this wrong. Early paleontologists, limited by Victorian assumptions and incomplete fossils, constructed a narrative of prehistoric stupidity that persisted through generations. Dinosaurs became cartoon monsters, lumbering through swamps with walnut-sized brains barely capable of eating and breathing simultaneously. That story was comfortable. It made extinction seem inevitable, almost deserved. Stupid animals die. Smart animals survive. The mammals won because they were better. Except that's not what happened. Dinosaurs thrived for 165 million years. They adapted to every terrestrial environment from polar forests to desert wastes. They evolved thousands of species with diverse body plans, ecological strategies, and yes, cognitive capabilities. Their dominance wasn't luck. It was success earned through adaptation, and adaptation requires intelligence. The revolution came gradually, then suddenly. CT scans revealed complex brain structures. Nesting sites showed parental care. Trackways demonstrated coordinated group behavior. Each discovery chipped away at the old narrative until it collapsed entirely. The dinosaurs emerging from this reconstruction are unrecognizable from their cartoon ancestors. They're real animals with real capabilities, navigating real challenges in complex environments. Brain size mattered, but structure mattered more. Troodon packed remarkable neural complexity into a skull the size of a baseball. Its brain-to-body ratio rivaled modern birds, and its brain architecture suggested visual processing, motor coordination, and spatial reasoning on par with intelligent modern animals. Was Troodon a genius? No. Was it competent, capable, and cognitively sophisticated? Absolutely. Hadrosaurs communicated through elaborate vocalizations, lived in massive social groups, and practiced extended parental care. That combination demands social intelligence, individual recognition, memory, and emotional bonds. They weren't just eating machines accidentally gathering in herds. They were social animals, navigating hierarchies, coordinating movements, and raising young together. That's complex. Tyrannosaurs, those apex predators we've loved and feared for generations, possessed brains specialized for hunting, enhanced olfactory processing, sophisticated vision, and motor control for precise strikes. They weren't mindless killing machines. They were strategic predators, possibly hunting in family groups, learning from experience, and adjusting tactics based on prey behavior. Intelligence shaped their success as much as size and teeth. Even heavily armored ankylosaurs, seemingly built only for defense, showed cognitive specialization. Their brains emphasized smell and spatial processing, suggesting navigation through complex terrain and possibly chemical communication. Different species evolved different cognitive strategies suited to their lifestyles. There was no single dinosaur intelligence, just as there's no single modern animal intelligence. Evolution produces solutions, not templates. Social behavior appears throughout dinosaur lineages. Colonial nesting, coordinated migration, pack hunting, herd defense. These behaviors create cognitive demands that drive brain evolution. You can't maintain social relationships without memory. You can't coordinate group activities without communication. You can't navigate hierarchies without recognizing individuals and tracking past interactions. Dinosaurs did all of this repeatedly, across multiple evolutionary lineages. Parental care, perhaps the most emotionally resonant behavior we observe in fossils, required planning, patience, and sustained commitment. Maiasaura adults didn't just lay eggs and leave. They built nests, protected eggs, fed hatchlings, and guarded juveniles for weeks or months. That's investment. That's attachment. That's behavior requiring emotional and cognitive sophistication we've traditionally denied to reptiles. Memory tied everything together. Navigation required remembering routes and landmarks. Social living required remembering individuals and relationships. Learning required remembering what worked and what failed. Parental care required recognizing offspring. Migration required returning to specific locations across years. Memory wasn't optional. It was fundamental to dinosaur success. Play behavior, though difficult to prove in fossils, probably occurred in young dinosaurs. Play serves crucial developmental functions in intelligent animals, teaching physical skills, social rules, and problem-solving strategies. If dinosaurs lived in social groups with extended parental care, their young had time, safety, and opportunity for play. And if they played, they learned in ways that enhanced cognitive development. Cultural transmission might have existed in limited forms, behaviors passed not through genes but through observation and teaching. Migration routes learned from parents, nesting traditions maintained across generations, hunting techniques demonstrated by adults to juveniles. We'll never prove dinosaur culture definitively, but the ingredients were present. Social living, extended parental care, behavioral flexibility, and memory. That's the recipe for culture in modern animals. Dinosaurs had all those components. Tool use remains speculative but possible. Some species possess the anatomical prerequisites, grasping hands or manipulable beaks. Whether they recognized objects as potential tools is unknowable. Organic tools wouldn't fossilize, but capability isn't proof, and we shouldn't claim behaviors without evidence. What we can say is that the physical potential existed in some lineages, and if environmental pressures favored innovation, tool use could have emerged. Emotions almost certainly influenced dinosaur behavior. Fear motivated escape. Aggression facilitated competition. Curiosity drove exploration. Pleasure reinforced beneficial behaviors. Even attachment, that most complex emotion, probably existed in species practicing parental care. Did dinosaurs love their young? We can't measure love in fossils, but they protected, fed, and nurtured offspring at personal cost. Behaviorally, that's indistinguishable from what we call love in modern animals. Consciousness, the deepest mystery, remains inaccessible. Were dinosaurs aware? Did they experience subjective thoughts and feelings? We'll never know with certainty, but consciousness likely exists on a spectrum, and dinosaurs fell somewhere on that continuum. Simple awareness at minimum. Perhaps richer subjective experience in the largest brain species. Birds are conscious. Dinosaurs were ancestral to birds. The cognitive architecture supporting consciousness didn't appear suddenly when birds evolved flight. It developed gradually through the theropod lineage, meaning non-avian dinosaurs probably experienced something, even if we can't characterize exactly what. The extinction event that ended the dinosaurs didn't just eliminate bodies, it erased minds. For 165 million years, dinosaurian intelligence had evolved, diversified, and succeeded. Then, in a geological instant, most of it vanished. The cognitive landscape of Earth reset. Mammals, previously limited to small generalist niches, inherited a world where the dominant minds had disappeared. We often frame this as mammalian triumph, but it was really dinosaurian tragedy. They didn't fail. They were killed by an asteroid. There's no lesson about superiority or inevitable progress. just bad luck and geological catastrophe. But one lineage survived. Birds carried forward the cognitive legacy of their theropod ancestors. Every crow solving a puzzle, every parrot learning language, every chickadee remembering food caches demonstrates inherited intelligence. Birds aren't primitive animals. They're living dinosaurs, continuing an evolutionary trajectory that began in the Triassic. When you watch a raven manipulate objects, or a jay cache food, you're witnessing dinosaur cognition in action. The transformation in how we understand dinosaur intelligence reflects broader changes in paleontology. We've moved from viewing fossils as static curiosities to reconstructing complete living animals. Modern paleontology integrates anatomy, biomechanics, ecology, and comparative biology. It asks not just what dinosaurs looked like, but how they lived, behaved, and thought. That holistic approach reveals complexity that anatomical analysis alone would miss. Technology accelerated this revolution. CT scanning, computer modeling, and biomechanical simulation provide tools our predecessors lacked. We can peer inside fossilized skulls, map brain structures, and compare them to modern animals with known capabilities. We can model how dinosaurs moved, what they ate, and how they interacted. Each technological advance refines understanding, replacing speculation with evidence-based inference. But the real shift is conceptual. We've abandoned the assumption that extinct means primitive. Dinosaurs weren't evolutionary rough drafts, waiting for mammals to show up and do things properly. They were successful animals perfectly adapted to their environments. Their body plans, physiologies, and cognitive abilities made them dominant for longer than mammals have existed. That's not failure, that's extraordinary success. Recognizing dinosaur intelligence doesn't require making them human-like. Intelligence takes many forms. Octopuses solve problems despite having completely different neural organization than vertebrates. Bees navigate and communicate using brains smaller than grains of rice. Intelligence isn't one thing measured on a single scale. It's a collection of capabilities that evolve in response to specific challenges. Dinosaurs evolved the intelligence their lifestyles demanded, and for many species, that was substantial. The spectrum of dinosaur cognition likely matched or exceeded modern reptiles and birds. That's a wide range, from relatively simple to genuinely impressive. Some dinosaurs were probably about as smart as modern crocodiles. Others approached or surpassed modern parrots and corvids. The diversity in body plans and ecological niches guaranteed diversity in cognitive abilities. No single characterization captures all dinosaurs, just as no single description captures all modern animals. What we've learned transforms these animals from monsters into creatures. They had personalities, preferences, and individual variation. Some were bold, others cautious. Some were social, others solitary. They formed relationships, remembered experiences, and made decisions. They weren't pre-programmed automatons. They were responsive, flexible beings navigating complex lives in challenging environments. Every discovery adds detail to this picture. New fossils reveal unexpected behaviors. Advanced imaging techniques expose brain structures. Comparative studies with modern animals provide context. The story is incomplete and always will be. We're reconstructing minds from bones, inferring behavior from anatomy, and extrapolating cognition from structure. Perfect certainty is impossible. But evidence accumulates, patterns emerge, and understanding deepens. The next generation of paleontologists will have tools we can barely imagine. More sophisticated scanning, better computational models, perhaps even preserved soft tissue containing neural structures. Each advance will refine the picture, correcting errors and revealing new complexities. The dinosaurs themselves aren't changing. They've been dead for millions of years, but our ability to understand them continues evolving. Dinosaur intelligence matters beyond academic curiosity. It challenges how we think about cognition, consciousness, and the evolution of minds. It demonstrates that intelligence emerges along multiple pathways, in diverse forms, serving different purposes. It reminds us that human intelligence isn't the pinnacle of evolution, just one solution among many. And it warns against underestimating animals simply because they're different from us. The legacy continues through birds, flying reminders that dinosaurs never truly died. Watch them, study them, and you're observing the descendants of creatures that ruled Earth for 165 million years. Their intelligence, their adaptability, and their evolutionary success echo in every chickadee, every crow, and every parrot. Dinosaurs didn't fail. They transformed, adapted, and persist in forms that still impress us with their cognitive capabilities. So were dinosaurs smart? The answer is yes, many were remarkably so. Different species in different ways, but intelligent nonetheless. They learned, remembered, communicated, cooperated, and solved problems. They weren't human smart, but they weren't simple either. They were dinosaur smart, which meant being perfectly adapted to being dinosaurs. And for 165 million years, that was more than enough. Their minds, as impressive as their bodies, shaped their world and left a legacy that still flies overhead, reminding us that intelligence takes many forms, and success requires not just strength, but thought.